Welcome, everyone, and thank you for attending the third day of the 2022 Summit on Drone Geophysics. It is a pleasure to see that we have participants from all across the globe in this virtual summit. This is the third annual Drone Summit, and in 3 years, what comes through loud and clear is that drone surveys are rapidly gaining momentum, and the technological advancements are keeping pace. The chair of this session is Francke, whom I will introduce in more detail in the second half because he's our keynote speaker for that half. Jan is a GPR expert with over 3 decades of experience. And I am Elizabeth Barani. I'm the geophysics domain expert at Sequent. A special thank you as well to all the sponsors of this summit. Our platinum sponsors will be doing a 10-minute demonstration in between the speaker talks once a day. Now, each presenter has 15 minutes to present and 5 minutes for questions and answers. If no time remains at the end of the presentation, the question can be answered later during the discussion period. And because of that, if you put questions in the Q&A window, please put the name of the speaker so that if we have to ask them at the end, we know which speaker to address them to. So all the attendees will be muted until the discussion period where they can be unmuted. You can be unmuted to ask your questions. All right, with no further ado, our first speaker, keynote speaker is Jasper Baur. Jasper is a PhD candidate in the Department of Earth and Environmental Sciences at Columbia University, studying volcanology with a specialization in remote sensing. He's the co-founder and president of the Mining Research Community, an organization that focuses on developing more efficient landmine and UXO detection methods for fusing unmanned aerial vehicles with remote sensing and machine learning to help combat the international landmine crisis. He has been working on landmine detection since 2016, primarily researching ways to improve the detection of the PFM1 anti-personnel landmine, which he will tell us what they are, because I don't know. He's also interested in the use of drones and sensors to monitor volcanic activities to better anticipate volcanic eruptions. Jasper is an FAA certified remote pilot and passionate about combining art and science through creating scientific illustrations. Jasper will be speaking about utilizing UAV-based imagery to identify and automate the detection of surface lain mines and UXO. Jasper, please take it away.
Yep, thank you for that really nice introduction. My name is Jasper Baur. I'll be talking to you today about how we utilize drones to identify different types of landmines on the surface. I am the co-founder of the Mining Research Community with my partner, Gabriel Steinberg, who's not here today. And we've been working on applying machine learning, drones, remote sensing to detect landmines. And I'm currently a student at Columbia University. So to kick off this session, I'd like to start on what are landmines and what is some background and why this is a problem. It's a really widespread issue. We see mines in over 60 countries and regions throughout the world. And this is just the most recent statistic, and it can even change in the future. They cause a lot of casualties and damages to people as well. Over 7,000 people were injured in 2020. And 80% of the casualties were civilians, half of them being children. So once a war leaves a region, mines are often left, and these really impact the civilians of that area. Besides just being dangerous, they're also a threat to local communities. You can imagine if there's mines in a farm field or anywhere else, it denies access to food, water, freedom of movement, and it really will stifle economic growth of these regions. Not only this, the mine crisis is actually expected to grow in the recent future due to ongoing conflicts in Ukraine and other places. We saw a really promising decrease in mine casualties from 2001 to around 2013, but it's actually started to rise recently. So landmines and UXO aren't a historic issue. They're still a current day issue that's affecting thousands of people's lives every day. So the traditional demining techniques, this is how most methods are for humanitarian mine action and clearing mines. It's usually using metal detectors and through a beep and prod method. So this is where you take a metal detector and a prodding mechanism, you go really close to the ground and you scan to see if there's any magnetic anomalies, and you try to detect landmines or UXO that way. This is a very slow process. If there's any kind of, let's say, a buried bottle or something else, that will induce a false positive and really slow down the process as well. On top of this, it's very expensive to remove mines. It costs around $300 to $1,000 to remove a mine, whereas producing one only costs around $3 to $75. So you can see 2 orders of magnitude more more expensive it is to remove mines than lay them. And that's really part of the heart of the issue. On top of this, mines themselves are becoming more evolved in the 21st century. They're becoming smaller, becoming composed of more plastic and less metal. So this means you have to turn the sensitivity of magnetic sensors or metal detectors up. They're also more randomized distribution. So instead of laying out particular grids of fields where people know the locations of, they might be scattered from above, and there's no records of where these mines are. So it's very dangerous and really hard to clean up afterwards. And all of these methods together really make mines and UXO much harder to detect. There's also a new breed of mines. This is really a sinister thing, and they're seismically triggered. One of these are the POM3. These are found in Ukraine right now. And essentially, you cannot approach these types of mines. If you get close to it, it will detonate. So traditional demining and manual demining, walking around, is not really safe in these types of conditions. And we have to think of new solutions to detect these mines without actually stepping into the field. And I'd also like to highlight the most dangerous part of the land release process. And land release is when you go in a contaminated, hazardous area, clear all of the mines, and then release it back to the community. And that's the ultimate goal of what we're trying to do. So the most dangerous part of the land release process is detecting the mines. Clearing them is actually much easier, not necessarily easier, but it's much safer. And once you know where the mines are, there's practices in place to remove them or detonate them in place. So I'll give a general overview of what we're trying to do to help assist current demining practices and utilize new methods. We're using drone surveys, so attaching thermal, multispectral, and visual cameras on a drone, doing an aerial survey over a suspected or hazardous area contaminated with mines and other munitions. Feed this process imagery into a machine learning algorithm. This machine learning algorithm already knows what the mines look like and has a generalized idea of where they are. And it will output coordinates of where the mines are in the image with certainties and type of munition. This will also provide a map from the UAV imagery that you can overlay with the coordinates of where the suspected mines are. So a little bit on the remote sensing theory. Visual cameras, anything, from your iPhone to a normal DSLR camera is on the drone. And these can be really useful for detecting surface lane mine and munitions. But you can imagine if it's buried or it's visually obscured, visual sensors aren't really going to cut it, but they can detect, a decent amount of surface lane munitions. We can also use thermal infrared sensing. This image here shown on the right will have different thermal anomalies, and this works in some areas because mines and munitions have distinct thermal anomalies from the surrounding environment. The emissivities may be different and the thermal conductivities are generally different. So we can actually identify mines in the thermal signatures and sometimes even shallowly buried mines using this method. We can also use multispectral imaging, look at unique spectral profiles, specifically plastics, and distinguish them from the surrounding environment. So I'll give you a brief overview of our remote sensing methodology. We're using commercial off-the-shelf drones. These are DJI Phantom 4s. We like using real-time kinematics to help have really highly georeferenced imagery without laying out ground control points. You can imagine that can be quite dangerous in a real minefield. But in general, off-the-shelf drones, because we want these to be consumer-friendly and relatively cheap for deminers to use. In terms of data acquisition, around 10 meters flight height, 80% overlap and side lap, so relatively high, and around 1 to 2 meters per second, so relatively slow, capturing the most robust imagery possible. Once the pictures are collected via the UAV, we process and clean them in a structure from motion photogrammetry software to produce georeference orthomosaics. So this is what a orthomosaic looks like. Sorry, New York City noise. This is what a georeference orthomosaic will look like. It is a really large, and if you can imagine, there's actually 23 different PFM1s. This is a small anti-personnel landmine inside of this image. And now you can start to see why machine learning may be useful in trying to identify the mines once you have a drone survey. We can start zooming in and you see different anomalies. Maybe these are leaves, maybe these are mines. And then eventually we get close enough and we've actually identified a PFM1 landmine. And this PFM1 landmine is only around 10 by 20 pixels by 40 to 50 pixels tall in an image that's almost 125,000 pixels. So it's essentially very, very small, 100,000 times smaller than the rest of the image. And what our ultimate goal is to draw a box around this mine and give coordinates and centimeter scale accuracy coordinates with the object, in this case, a PFM1, and its certainty score. So in this case, it's quite certain, 99%. So now we're using machine learning to help automate the detection from remotely sensed imagery. We're applying a faster regional convolutional neural network called a faster RCNN, and that's chosen for its accuracy in speed and small object detection. Essentially, the neural network creates a generalized model of an object through feature extraction from convolutional layers. What that means is basically it starts looking at different features of the mine, such as the edge, the shape, the color, and creates different vector feature spaces to identify what a mine looks like and create a generalized model. So this is essentially how we train the neural network. There's a training set. So these are hand-labeled imagery. We draw bounding boxes around the mines and identify what they are. We provide this training set into the blank neural network, and then it goes through a training period. After this, it is a trained model, so it actually has an idea of what the mines look like. To assess the accuracy of the neural network, we withhold some data, generally in a different environment, well, with the same type of mines and munitions, and then put this into the trained model through testing, and then it will output predictions of where these unseen mines are and give us locations and coordinates. So what does our data, our training set look like right now? We have over 145 labeled RGB orthophotos. We have over 10,000 labeled munitions in 6 different environments, from grass, high dirt, high vegetation, gravel, salt flats, and over 50 different types of landmines and UXO. We also have collected multispectral and thermal orthomosaics as well. So some results from the neural network is we have now an 80% accuracy across 8 munition classes. Something that's pretty unique is we actually group similar type ordnance in the same group. So although we have 50 different labels for the different types of mines and munitions, we actually group them all in sort of similar groups. And there's one of them would be projectiles. And in this case, we had an 86% detection rate for projectiles. Some of the other ones, such as hand grenades category, had 76% accuracy, but overall an 80% accuracy in detecting these types of munitions. In a blind trial, so this was conducted last month in Budapest, a EOD team laid out different types of munitions and UXO in a field for us. We had no idea where the mines were. Then we flew our drone over the field, collected the imagery. The drone survey took around 5 minutes for around 400 meters squared, generated a map and locations of the mine through the neural network in around 20 minutes, and the entire method was performed offline. The results of this blind trial had 20 out of 23 UXOs detected with an 87% accuracy. So some implications of this research is, I mentioned in the background slides, seismically activated mines, and these are really unapproachable. So having a drone survey as sort of a first order approach to assessing a mine field can be really useful to detect these seismically activated mines and help save people and miners in the field from approaching them. Additionally, we hope that this method can assist the miners in the field to help prioritize areas of clearance. Oftentimes, there's these things called suspected hazardous areas, which are essentially areas that may or may not have contamination of mines and other explosives, but we're not fully sure. And you spend a lot of time actually demining areas that have absolutely no mines in them. So if we can do a drone survey, feed it into the machine learning algorithm and output coordinates of where the mines are, it may not and likely will not detect 100% of the mines, but it can give you some idea of the density. Let's say one field has 100 or 6 or 7 mines detected, the other has 0. You can probably prioritize the area that has known contamination. On top of this is relatively low cost. We're using commercial off-the-shelf drones and open source software. It's fast and it can reduce the danger for field operators. It's quite efficient and can be performed offline. So our future work, we're looking to work with Bomb Techs Without Borders. It's a nonprofit organization that is now boots in the ground in Ukraine, detecting mines and UXO there. We're also trying to collect more training data in contaminated regions. We're planning a trip out in Southeast Asia to basically collect more data to have it more catered to different regions such as Philippines or Cambodia. We also are working on developing a multi-channel neural network. So this is not inputting just visual imagery, but we can also overlay thermal and multispectral as more channels that can cross-correlate detection and help reduce our false positives and false negatives. And lastly, we've seen a lot of really interesting talks, and we'll see a lot more today on integrating magnetometry, EMI, and GPR surveys. So I'm always looking to collaborate and add additional data streams for remote sensing detection of landmines. Thank you.
Yeah, actually, you do have a few questions, and I think we have a few minutes. First question, 2 questions from David Rose. What is the percentage of false positives and false negatives, and how do you deal with vegetation?
Okay, so these are good questions. I'll start with the false positives and false negatives. It's really subjective. So you can create an algorithm that has, maybe a higher accuracy and includes a lot more objects that may or may not be mines. And that's really what I opt to do. I'd rather have a lot more false positives and much fewer false negatives than having, maybe a higher overall accuracy, but you have more false negatives, because those are really what's dangerous. So let's say we have, I'd rather have 50 false positives than miss a single mine in the field. So what we do is we make the algorithm sort of less sensitive and give us more. And sort of an easier way to clean it is you click through, and we have a program that will show you bounding boxes, and you can actually visually confirm if they're positive or negative. So that, not necessarily a quantitative answer, but that's really the best way, I think, around that. And with vegetation, it really depends. So this picture right here is actually in a quite high vegetation area, and they can be fully visually obscured essentially if mines are buried here or even on the surface sometimes. In shorter vegetation, they can often be detected. So this is something that we're working on now, trying to implement more thermal or essentially magnetic based imagery to detect in high vegetation.
Question from Ted Ash. What is your depth of investigation for the different classes of mines and UXO, and how deep can you see?
So these are mostly visual imagery. We did do some buried trials. What we found is it's quite subjective, but generally for thermal imagery, it can reach in only a few centimeters deep. So not too deep. And it depends on if the soil is saturated or not with water, if it's a desert or if it's a farmland.
Jeff Petfer is asking, what is the limitation on depth of burial? Would you most of the time be looking for disturbed soil anomalies rather than hardware?
Yeah, so detecting presence of mines is a big thing. So you can identify craters or disturbed soil. Like I said, visual imagery is not going to penetrate at depth, but you can identify areas that might have looked like recent burial. This only works in areas that have, recently deployed mines. And generally, humanitarian mine action is in post-conflict nations where this has been around for decades or a lot of years. So oftentimes it's quite hard to see signs of burial, but in some regions like Ukraine right now, you actually can.
Next one is from Heidi Mayers. Have you explored any other machine language techniques such as scattering transform networks that don't require large training data sets?
I haven't explored that. We have explored sort of simpler supervised class algorithms and maximum likelihood, but really the convolutional neural networks are way more accurate than those. I haven't done any supervised learning or clustering type ways. So, I mean, it could be interesting, but we're getting really good accuracy with essentially training data. So I haven't really explored other ways because of that.
One last question. Ed Penian is asking, for safety purposes, is detonating the seismic triggered mines using a ground shaker of some kind of or small charge feasible?
I think it is feasible, actually. I was thinking about this too. This is a good crowd to talk about, shaking and all that seismically activated mines. So I think it is possible. I'm not sure if it's being done yet. We've had some ideas about trying to do that.
Thank you.
I actually have one more question. We have a minute and a half, so I'm going to throw it in here. Jasper, I've had the misfortune of having to work with UXOs in West Africa quite a bit. And what I've found is that they never land, particularly the airdrop ones, they never land right side up, particularly the missile type ones. They are intended to bury themselves in the ground. So when you look at them from an orthophoto standpoint, they're never sort of nice and flat. In West Africa anyway, in the soft soils, they tend to go like this. And they look different from the top down. How do you deal with that sort of real world situation? And, they're very rarely nice discs.
Yeah, it's a great question. So in our training data, I mentioned there's different environments, essentially trying to get different variants. And we do the same thing with orientation. I didn't mention it, but we'll take sometimes just the tail of a mine or the tail of the projectile and stick it straight up, stick it at different angles to try to get, improve the data. It's not even augmentation. It's just improve the training set. There's also data augmentation we can do to rotate them around. But yeah, it definitely has to be accounted for.
Lovely presentation. Thank you. And I'm very glad to see that there are nonprofit entities that are interested in demining. Thank you, Jasper. We are going to move to the next speaker. We are just in time. Lovely. Bart Hoekstra. Bart is the VP of Business Development at Geometrics, and Bart will be presenting on improving drone-based magnetometers for UXO surveys. Bart, please share your screen.
All right, thank you. Thank you for that introduction, Elizabeth. Good to see you again. So yeah, my talk's going to be about some of the efforts that we've made at Geometrics to improve our drone sensor for UXO type surveys. So there's clearly been a lot of interest in deploying magnetic surveys from drones. Magnetic surveys have been used for basically since UXO has been developed or mines to detect unexploded ordnance, and there's a lot of benefits from deploying it from a drone. You get increased survey productivity, which means you can clear land compared to people walking back and forth on a grid. And as mentioned before, there's some significantly decreased risk compared to towed or hand carried systems because we don't have boots on the ground and can potentially cause problems. I think, in some areas too, when we talk about archaeology, a lot of times you're trying to get into areas which may be active agricultural areas. And so, you might be trampling on crops during some seasons. So it's nice to get our sensors off the ground. But there's some significant issues with deploying magnetometry from drones. There is the primary one is really how close can we get to the surface? And typically for towed or hand-carried magnetic signature, we're trying to get a foot off the ground. And so that's quite difficult to do from a drone, both for safety reasons and operational regions. But I think progress is being made by the drone manufacturers. That's not going to be the focus of our talk. But then the other issues are, from our perspective, are noise due to the sensor platform and movement within the field and how we can reduce that. The magnetic signature falls off as the third from your target. So how do you decrease the noise due to platform movement so that you can increase your signal noise on target detection? And then the other thing is the positional accuracy of a sensor suspended from a drone platform. In a lot of cases, if we're talking about buried targets, we want to give the people that are going to be investigating that positional accuracy down to centimeters, ideally something like a shovel width. And so if we're relying on a suspended sensor platform below a drone, we may not have that kind of positional accuracy. So these are the kinds of things that we've been trying to address over the past several years. So improving positional accuracy, there's a couple of challenges that we have that probably aren't that critical. There's a billion different kinds of GPS solutions out there, but we need ones that are very lightweight because that's very important for this application. And also we need low magnetic signature systems, and that turns out to be quite difficult. That's not the first thing that GPS manufacturers think about, is how much ferrous material do they have in the antenna. And so that required getting a lot of stuff in-house and doing a magnetic signature tests on. And the other challenge that we had too was that when you're starting to fly platforms close to the ground, then multipath rejection becomes more important. Typically with drones, we're flying them up above the canopy. We're not flying them in and around buildings, and we're not flying them that close to the ground. And so you don't get GPS multipath, which is what arises when you get GPS signals reflecting from buildings or trees or from the ground itself. And this can cause significant decrease in GPS accuracy. So that's not something that drone manufacturers typically worry about, but we have to in this case. So that was the other critical thing. So what our solution was to go with a optional antenna that we can mount on our platform now, that is a helical antenna, and it basically allows us to look at the polarization of the GPS signal. It comes in sort of in a circular form. And by using a helical antenna, we can do a pretty good job of rejecting reflected signals, because when they're reflected, they change their polarity. And then, of course, we can upgrade our electronics. This has been, there's a lot of effort being put into making good low power GPS electronics. So, even without RTK, just by using an external antenna and new electronics, we can significantly improve our positioning accuracy. Here we are walking up and down the street outside our building, and the green was our previous antenna, and you can see we've got terrible accuracy, which is completely insufficient for UXO activities. The red lines are what we can do now without any kind of RTK base station correction. So we think with internal antenna, we're about 1.5 meters, 50% circular error probability. So that's much better than the 2 to 3 meters we had. If we apply RTCM, we can get that within a meter within our internal antenna. And then with the external helical antenna that you can show here, we are probably within 3/4 of a meter without RTK correction. So now we've got significantly improved positional accuracy. But here's what we can do with RTK, which is great, right? Here we are. We basically walk back and forth along the road here with hand carrying the mag arrow, and it's great. And you can see that even in we have trees here, we have buildings here, and using the RTK corrections with the multipath rejection, we can get very, very excellent positional accuracy. We're thinking 2 centimeters with 50% circular probability. So well within the shovel width of what we're trying, our objective was. But RTK comes with its own set of issues, right? We need a radio transmission if we want to do RTK. That requires a radio receiver on our platform, which potentially increases the magnetic signature and causes more noise. It also increases the power requirements on our platform. We have an internal battery because we're trying to make it as independent of a platform as possible, and so it causes issues if we want to have a real-time radio, and then you have line of sight issues and all of that. So we also have the ability to use NTRIP, which is basically a way of sending RTK corrections over the internet from base stations collected at various locations. And that requires probably a cellular connection, which is definitely not always possible. And then a Bluetooth connection to the GPS chip on the platform. So that's possible in some areas, but not always very practical for a lot of places. And lastly, what we have is probably what's called PPK, which is post-process kinematic. And that is basically where we store information on the on the sensor platform itself from the GPS chip. It requires quite a bit more information than just logging a EMEA string, but hey, memory's cheap, so let's just throw it on there, and then we can download it later. It takes a little bit more time to download, but then you can combine that with data from either base stations available over the internet or from a base station you have yourself nearby, and you can then get accuracies within centimeters. The drawback to that is that you don't know in real time what your positional accuracy is, and a lot of times if you're flying in close to dense vegetation, that could become quite an issue. So that's our main concern, but and the software is kind of clunky too, but we're working on improving that. So we think we have the positional issues solved for doing UXO surveys. But here you can see why the positional issues are important. Initially, we thought, well, hey, you could use the position of the airborne platform to sort of figure out where your sensor is, but really, what we found is for the best sensitivity for a magnetic platform, we need to be about 10 feet away from our airborne platform. And so you get, there's significant change in position from the airborne platform to our sensor platform. So, we need that. And then the other thing that happens is that when we suspend it like this, we can't use a rigid suspension over these distances. So then our sensor platform becomes, starts swaying and moving back and forth, and that can induce what we call heading effects, which is basically where we get noise in our measurements due to the orientation of the sensor platform. And there's two main contributions to that. One is noise from the things like ferrous materials that are within our electronics. That's almost impossible to get rid of entirely, but we're very careful about how we design our electronics to reduce that. But also there's even at 10 feet away, there's a magnetic signature from our drone. And so as that flies through the Earth's magnetic field, it causes noise based on its orientation. And then the other effect is from basically fundamental physics of our measurement system. We use cesium vapor cells illuminated by lasers, and basically that's also somewhat sensitive to orientation within the Earth's magnetic field. So it's really unavoidable part of magnetic surveying for the most part, unless you go to some other different types of sensors, but they have other trade-offs. So here you can sort of see the effects of heading on our magnetic data. And this corner up here shows a flight path from our system. And then the blue is the magnetic field. So this is measuring the total magnetic field of the Earth's magnetic field, sorry. And so what you can see is, especially where you have areas where you're turning around, then we tend to get things like swaying of our sensor platform, and you'll get increased noise here. This is nanoteslas, so it's about 2 nanoteslas for each grid square. So it's a significant amount of noise depending on the sensitivity you need for that. But what we've developed, I mean, people have been putting magnetic sensors on platforms for a long time, and so people have worked out ways of sort of compensating for the effects of this. And here's sort of the results of what we've done. The blue line is our original data, and then the red line is the data after compensation. And so now you can see significant improvements in the data. Clearly, we have less noise from the platform twisting around. And really, what's critical for us is now you can see very small anomalies in the green circled areas that really were not visible at all from just looking at the raw data. The rule of thumb that we use is that typically we can get rid of about 90% of the noise from heading effect with the doing compensation data. And I think that's shown here. So this is a survey area. This is required offshore Florida, looking for shipwrecks in shallow water. So we needed fairly good data for that. The total peak-to-peak scale on this is about 9 nanoteslas. So this is very quiet data. The first thing you can see with just the raw data is that we have a significant effect just based on line orientation. And that's typical. And that doesn't necessarily have to be gotten rid of via compensation. You can do some line leveling by breaking it up. But anyway, but you also see going along the lines, you can see small variations that look sort of rhythmic, sub-nanotesla type noise that is due to our sensor platform swaying back and forth and maybe pitching up and down a little bit too. But after compensation, we can see significantly better data quality. And so now you can start seeing anomalies here that really are on the half nanotesla, which is as good as you can get from basically towed platforms on the ground. So I think this is clearly a very significant improvement in magnetic data, and it really becomes critical for a lot of UXO when you start talking about trying to find buried objects and smaller buried objects. The noise is critical. So quickly sort of run through how we do it. We have an inertial motion sensor on our platform, so we can measure pitch, roll, yaw. We actually break that down into azimuth, so heading of the platform, and then the polar coordinates of the platform. So mostly that's yaw, but also can affect takes into account pitch. And then we have that. We have our sensors. We actually have 2 sensors on this platform oriented perpendicularly, so we can avoid dead zones and dropouts. And here you can see the dashed line represents our azimuth, and our blue line represents our magnetic data that we measure, and we can see that, that the azimuth is the primary contribution to the heading effect. So in order to do this, we need to do a compensation flight before we start acquiring the data. This can be done kind of once per survey area because it will change depending on where you are in the world. We'd like to also, and this can be done in 10 minutes or so. And there's, you can do a cloverleaf platform or sort of emulate your survey pattern. And it's also very important to have a good base station correction to remove the diurnal effects from your compensation data. The processing flow has basically been to acquire a compensation flight before you start surveying. Then you need to process your compensation flight data, do a base station correction, sort of do a QC check on your data. One of the most important things is sort of evaluate where you have most of your data so that you can say, yeah, most of my data is clustered along the primary orientations of my survey lines so that I can do a good job of correcting my survey lines. And then we compute compensation parameters and save it to a file. Now there's a variety of ways of computing compensation parameters, and this has been active research for quite a long time since we started putting magnetic sensors on things like fixed wing aircraft or helicopters. Ideally what we've discovered for these type of applications that we just kind of build a lookup table, do a least squares fit to our data and come up with basically just a correction for heading versus compensation factor. Once you've acquired your data, you need to pre-process your survey data. You need to apply a low pass filter to it typically and get rid of noise. Then basically here you can see in the lower corner, just sort of ensure that the primary, this is showing a clustering of azimuths. So, this is our survey data. So we're going, one direction, coming back the other. So we've clustered with our positioning, and then we should see similar clustering in our compensation data. And then we can apply the compensation and do that. So right now that's all available in software that we provide with the system on request. So, we think it's not too bad. It's not quite a lengthy process. It's not lengthy, it can be done in minutes per survey grid. So I think, if there's other questions, I'm trying to find my clock. I don't really have it here. But anyway, that there's a publication available online where we discuss some of this in more detail. People can have a look at it. I'd like to thank people that did a lot of this work for this. Ji Zhang here at Geometrics, along with Mark Prouty and Kevin Hurley, and then Frederick Conselman and Ryan Folks from the University of Florida, and Matthew Lawrence from NOAA. So with that, I'd be willing to take any questions.
Thank you, Bart. That was such a comprehensive presentation on the workflow. I may have missed it. Did you elaborate on the rate of data collection? Because your mags can collect up to 1,001 kilohertz.
Right. Yeah, we can collect up to kilohertz. I would say, how much data you keep after that, it depends on sort of the speed of your platform and your survey and how small a target you need. In this data set, we downsampled to 20 kilohertz, and that has basically just to reduce data volume, because a kilohertz data, if you collect several days of that can add up, and so people tend to prefer downsampling.
Thank you. There are a few questions. I think we have time. Do we have time, Jan?
We are a little bit over time right now.
Okay.
Okay.
You can look at the questions, Bart, online.
Okay.
We will then move to the next speaker, Maximilian Orman-Kollmar. Maximilian is a PhD candidate at Thayer's School of Engineering at Dartmouth College, and he will present on drone-based time domain electromagnetic induction for subsurface unexploded ordnance detection. Maximilian, please take it away.
Oh, good morning. As Elizabeth mentioned, I'm a PhD candidate over at FAIR at Dartmouth College, and our group is focused on electromagnetic induction and subsurface sensing, with my particular project looking at subsurface sensing for unexploded ordnance. So a little background is why we're looking at this, why is this an actual question at all? UXO are prevalent global danger, both humanitarian and environmental issues. From a humanitarian standpoint, these are basically detonations that are just waiting to happen. When an artillery shell or mortar shell gets fired, it doesn't explode, it gets buried into the ground and lay there for decades or even a few days. And when it detonates, there's civilian casualty. According to a US State Department survey, came out this year, that since 1993, there have been about 4.2 billion US spent on global cleanups. And that's just looking at the time being spent to inspect the ground, not just looking at interrogation time. Also, there's another danger from chemical leaks with these UXO rupture. There's a chance of the explosives leaking into the ground, so you have soil and water contamination. And as I just mentioned, there's that huge cost, but that's again just for interrogation. Now looking at also getting rid of these UXO. So what's the current standard of solution? Right now, there are all mainly handheld solutions. So you have an operator on the field going through in grid patterns, interrogating areas that are potentially laden with these explosives. A lot of the ones that are currently being used are just audio feedback. So if you go over and they detect something conductive, they'll get a beep, which means that an operator has to flag every single mark they get. And for a lot of these sites, you have, for every 100 flags you get, there's one UXO. But every single one has to be interrogated because you don't know if it's a false positive or an actual positive. Excuse me. So other solutions that exist that use electromagnetic induction or EMI are often very, very heavy and very, very large. So that makes them very difficult to use for longer periods of time, as well as harder to use in terrains that aren't smooth. So if you have a lot of rocks, heavy vegetation, so that makes it unwieldy on both senses. So our proposed solution is having a UAS mounted solution, which we can actually use to discriminate between clutter and well as different munitions. So why EMI? EMI is very fast and non-intrusive. You can get a response in the order of a few minutes of having a stationary system, and you don't need to dig into anything, right? There's no need to have disturbances of the ground, which, as I believe Jasper mentioned in his talk, there are seismic explosives now. So digging in and interrogating physically is a danger. Secondly, the physics for this are well defined, and simulation and verification is relatively easy to accomplish. So you can actually test your solutions before going into the field and have them online. What is this physics? So essentially what happens is when you run a current through a transmitter coil, creating an electric field. As for Maxwell's equations, we then get a varying magnetic flux produced by this. As the flux penetrates the ground, if there's nothing there, it just dissipates. And so there's no response from an empty area. But when there is a target, a metallic conductive target, you get an induced field across it. As with all Maxwell's equations, you can see in the fourth one that change in magnetic curl across it will induce an electric flux as well as surface current. This secondary induced current this surface current will induce a secondary current to impede this, as by Lenz's law, where we have any newly created field will be impeded to stop this creation. That secondary electric field will produce a secondary magnetic field going back up, which we can read through our receiver coils. These receiver coils store the voltage and store that into our biggoscope as a set value, which we can then use to process and detect data. So the general workflow that we have going on is first you have a classification process. First you have data acquisition. On the left screen here, we have an older system, a handheld variant. But you can see that it's going over the field, and we have various targets beneath this, clutter and UXO. We then take this collected data and run it through an inversion process, because this is an inverse problem. We don't know what is below us, and that's what we were trying to solve. This inversion will give us back inherent properties for each target, which we can then further go in and cluster with a decision process. So given these features, we can then say with high certainty that certain areas are high clustering, and certain areas are low clustering, versus some areas being just clutter. So what do we actually use? The sensor that we used consists of 4 transmit coils and 4 triaxial receiver coils. They're all co-located. These triaxial receiver cubes contain receiver coils that can sense X, Y, and Z components of that secondary magnetic field we get from our target. We suspended it below a carrier HX8 Harris drone, which is a larger drone, but currently the system weighs about 14 pounds due to size limitations of needing these transit coils. And so we're working on making it smaller and more compact as part of our process. So here it is. We call it the ultralight electromagnetic array, or ULEMA. Specifically, this one's called the ULEMA Air. And you can see here with my colleague's iPhone 12 for size scale, we have our 3 interior transit coils. These purple styrofoam circles are keeping that tight in place, as well as a 4th one going all the way around it. These cutouts, as well as another one buried beneath this carbon fiber sheet, are for our triaxial receiver cubes. The carbon fiber sheet serves both as a sandwich to keep our system rigid and steady in flight, as well as to elevate the electronics outside of the interior. Originally, we had planned so that all this would be inside the system, so it would be completely sealed off and we wouldn't see anything from the outside. But in testing, we realized that we were getting a lot of noise from the electronics. So we decided to move it out, and that actually cleared up a lot of the noise for our signal. What we did was we had a set of targets laid out, and we suspended our sensor below the drone. We gave it about 10 feet, both for noise clearance issue, so we wouldn't get noise from the drone itself, as well as to allow our operator to have room to maneuver the drone around and not get tied up in the sensor itself. We made several 2-pass runs over all the targets, as well as collecting some stationary data over a single target at a time. The targets we collected range from the left here from an 11 centimeter diameter shot put all the way up to a 155 millimeter target, which is a 155 centimeter diameter target. And again, I have my colleague's iPhone 12 next to each target for a size scale. Typically, we use the shot put for calibration for our sensor, because the intrinsic parameters will be equal on all 3 axes. But we decided to throw it in here just to get a smaller target for classification and verification. So now I've got a few videos of the flight I want to show. There we go. So this is our sensor flying up. And as you can see, we needed a bit of extra room on the hangars just to give us enough space to actually get up above the sensor, as well as having that safety issue from noise. And here we have it in flight. It's currently being operated by a human sensor, a human operator, as you can see back here, which is part of why we had this much oscillation in our flight. In trying to keep a steady flight speed, it was very hard. So we had to stop and start at certain points as we were trying not to overshoot targets, trying to keep it not going too fast. And so that kept us going this oscillations, periodic motion, which we are trying to eliminate as we go on further in this testing. So you can see one of our targets there. They're all sort of buried in the grass. But that doesn't affect our detection. The penetration is basically for conductive and non-conductive objects. Our second flight, we did another dynamic pass. We also had some stationary collections where we would hover over a target and go up and down just to collect a different kind of data set. I'm trying to find. So this is us stopping, then keep going. And again, as you can see, we get the oscillation, which is very difficult to deal with at the moment. Is this? Then here we hover over it for about 30 seconds and start descending over it to get closer and closer, and then going back up to get a little further away just to see the response in the data. And finally, our third flight, we lifted the targets out of the ground just to have them more visible for our operator. Easier to see where you're going as opposed to kind of position yourself side to side, front and back, with people on the side in front of you telling you where to go. So here we have it making our first pass as we try and center it. And so you can see there's a lot of oscillation as we try and keep it steady, but it's very, very hard to keep that in line. And here should be the hovering example, where you hover over an object, then try and descend to collect that response. So what does that give us? Here is one of the recordings from our flight 1. As you can see, there's a lot of noise coming from that oscillation, but we still have the distinct peaks, for example, up here, down here is a very clear one, and up here. So this graph shows all 4 transmitters looking at the z-directional receiver components. This is over one set time gate, and we can see all the data points being collected as we fly. And so again, this is all very well and good, but what does it actually give us from that? So this is the decay response from that secondary magnetic field. This is an example of a non-detection. There is nothing below us. The field decays down to on the order of 10 to the minus 3 volts per amp very, very quickly in the order of a millisecond. And so from this, we can say that nothing was found below the sensor at this point. Compared to this response, where you can see that the magnetic field remains high and sort of decays down logarithmically from 10 to the minus 1 down to 10 to the minus 3 over a time scale of 10 to the minus, or about 100 milliseconds. This indicates a detection. So from our second flight, where we have much cleaner data, this is from, I believe, one of the up and down sections. We have very clear detection here, spike here, detection, nice cluster here. And again, another few examples of these very clear, very nice detection visualizations. There's one from one receiver, from one transmitter, another transmitter with the same receiver level. And here's another one, which is again, very, very distinct, very easy to see. Finally, here are 2 different detections from our records from our flight 3. This is one of our hover, descend, and ascend sections, where you can see this high peak kind of stays where it is, the detections. And this is just our dynamic flight, where we still get a little bit of noise from that high swinging, but again, clear detections are visible. Again, one more comparison, no detection being visible here, compared to high detection being visible here. So further steps we want to take into place is stabilizing that flight. So working on removing that oscillation, whether it be with using waypoint missions or getting some kind of damper set into the rope system. Other one is you didn't see it in the videos I showed, but what we had to do was turn on the system, plug in SSH in with a computer, and start collecting the data, and then go away, start the flight, and start flying. But what we want to have it do is, what we want to be able to do is connect from a remote system live, which we have a different system that actually can do that right now. So we're working on improving our interfacing connection right now. As mentioned, we want to start using waypoints for data collection as opposed to having a human operator, just because that would make it easier to fly it more consistently and be able to set areas to go over as opposed to trying to set it, stabilize and by hand. And right now what we have to do is post-process the data on our own. We want to start implementing machine learning algorithm to let the system fly and then initiate detections on its own, as opposed to having to do it manually. And on the last point, we were looking at not just having our U-limit air system, but having it integrated as both possibility for air, handheld, or robotic integrated systems. We have one that can do the last 2, and we have our one first. So we're trying to streamline it and get into one system to do any range of missions we need from there. Thank you. Any questions?
Hi, there is a question online and we have a couple of minutes, I think. The question is from David Rose. How do you compare this method to the existing one using 3D polarizability? Is a library comparison of the measured decays during the flight with the responses in that laboratory done? So the first one is, how do you compare with 3D?
So that's actually what we do. So I guess I didn't say explicitly, but this inversion slide, the inversion, what it gives us are the polarizabilities in 3 axes, X, Y, and Z. And we compare it to a very, very large data set that DoD has. Thankfully, we are partnered with the Polar Regions Research Engineering Laboratory up at Hanover, New Hampshire, with the Army Corps of Engineers. We have access to that. So that's what the machine learning will come in, is that right now what it does is we have our polarizabilities and we cycle through this library and connect and sort of target what we think the system is based on that. And what we want to do is we have this huge training set. So we want to train an algorithm to detect something live. And we can see that, it's a cluster, or it's a 1.5 UXO, or it's something else. And for depth of detection, for this system, we're still working on that. We theoretically can do 11 times diameter. For our handheld variant, we've gotten responses of up to 2.5 meters, I believe, below ground. So not in a flyby yet, but we're working on clarifying that a little more as we go.
Thank you. A quick question. What's the flight time? Because your system looks heavy, so probably that eats into the flight time.
So right now, I'm not super sure on flight time right now. I'm not yet licensed for operations, so I'm still working on that with our current operator. But we had about 20 minutes, I believe, per battery that we used, and we got 2 flights, and so we had about 40 minutes of flight time with a different set of batteries.
Thank you. Thank you, Maximilian. In the interest of time, we will move now to the last speaker of the first half. So our next speaker is Dr. Wei Liu of the School of Electrical Engineering of Chongqing University. Wei will present on a rapid investigation of anomalies in water by UAV transient electromagnetic technology. Thank you. Please start, Wei.
Thank you for inviting me. I'm very glad to be here to join the 2022 Summit on Drone Geophysics. The topic of my presentation is the rapid investigation of underwater anomalies by unmanned aerial vehicle transient electromagnetic technology. My presentation will include these 4 parts. First, some background information about this research. Second, the theoretical basis and finite element simulation analysis of our local method of detection. Third, the instrument design and complex system composition. And last, experimental results and our future goals. Land structure detection using electromagnetic wave propagation characteristics for near-surface anomalies has attracted a lot of attention in different areas these days. Time-domain transient electromagnetic method typically employs 2 different multi-channel coils, the latter of which is used to transmit the time-varying current to generate a primary electromagnetic field, and the other receives the secondary field-induced voltage from the eddy currents of subsurface conductors. As shown in these 4 pictures, maritime research and rescue, unexploited ordinance detection in complex offshore environments, military exploration of offshore areas, and river salinity monitoring are need a fast and valid long-destructive detection tool. It should not only have high resolution, but also be efficient. The integrated structures of transmitting and receiving coils are generally employed in conventional TM detection devices. The tau TM system shown in the upper right picture is used for river salinity detection. However, an overlong offset more than 9 meters between the transmitting loop and receiving coil has made it hard to operate the ship and obtain valid data steadily. Airborne transient electromagnetics have become one of the most popular ways for deep geophysical perspective due to its rapidity and high efficiency, because it's unsuitable for near-surface exploration due to its high cost and difficulty in operation. In the final picture, the UAV TM system can be built as a miniature version of the airborne Transient system. However, the heavy load and short power supply time for single flight make it limited for many applications. So we put forward a rapidly magnetic measurement field combining grounded magnetic dipolars and aerial UAV scanning. The separate magnetic dipolar source on the ground ensures large magnetic moment transmitting. The high precision induced voltage sampling is used for long distance observation. The GPS modular and constant temperature crystal oscillator are used to realize the separate magnetic dipolar this dipolar source on the ground ensures large magnetic moment transmitting. And the high precision induced let's look at this picture. The left figure shows a electric model in which a map cube with a side length of 0.3 meter and is buried 200 meters away from the MDS on the y-axis. The comparison results of finite element simulation in two figures on the right show that the early secondary field above the low resistive anomaly is obviously different from that of the homogeneous half-space model. This explains the effectiveness of the scheme from the electromagnetic principle. This figure shows the relationship between the secondary field distribution and the observation height in an appropriate observation time period. From the attenuation curve and the height lines of flux density, it can be seen that when the observed height exceeds 10 meters, not only does the flux density decrease by more than 10 times numerically, but also the reverse sign characteristic of the field intensity in the measurement plane will disappear. So our suggestion is that during the actual measurement, the flying height of the UAV should not exceed 20 meters and the receiving coil should be within the 10 meters H range of the outer surface. And then the design process of the instrument is shown here. First, we designed the 2.5 meter diameter multi-turn coil to generate current pulses and time-varying magnetic fields. The size of the coil is not large, mainly for the convenience of transportation. The increase of transmitting magnetic moment mainly depends on the increase of coil length and the transmitting current. A bipolar current pulse power supply with resistant charging in the late terminal period is designed to achieve a large TX magnetic moment for the relatively small exciting coil. The maximum transmitting current is 300 amperes. To observe magnetic fields in multiple directions above detection area, 3 component built-up coils are designed to induce voltage from the 3 original planes. A low-noise programmable amplifier is placed at the front end of the signal processing circuit to increase the amplitude of the effective voltage signal. A wireless communication modular is designed to receive and send relevant data between lower controls and upper pieces of wire. The left figure shows the construction site of the MDS-TM receiving system to reduce the influence of rotor rotation and other mechanical noise of the UAV on the receiving signal. The receiver is suspended 2 meters below the UAV, and the induced coil is suspended 6 meters below the UAV. Finally, I will show you the experimental results and our future research direction. On the measured waveform of the 3 component induced voltage and the intersection of all dotted lines in the direction in the detection area as extracted by comparing RTK coordinates, and the results are shown in this figure. The voltage of early turn of stage above the anomalies body is significantly lower, and it's also reversed earlier than the other measurement points because the eddy current generated by the onward metal body slows down the attenuation of the magnetic field. This figure shows the position imaging of the induced voltage scanning. Obviously, the abnormal metal body can be quickly located by measuring the induced voltage during the early turn of stage. The mapping work is completed quickly after scanning the target region because the induced voltage is extracted directly and simply normalized. The detection result verifies that the electromagnetic measurement system can realize fast location of underwater anomalies due to a portable scanning device and simple mapping steps. And then we are going to do an extension of that. First, the multi-source system can increase the signal strength and extend the operational area of a single flight. Second, the scanning efficiency can be improved by using unmanned aerial vehicles to carry the receiving area. And last, an inversion algorithm should be developed to obtain the depth information of anomalous bodies, and the fineness of the field can be further raised. That's all. Thank you. Thank you very much. And if you have any questions or suggestions, contact me anytime, please.
Thank you, Wei. There are no questions in the Q&A window. Can you bring up the illustration of your system? Where is the GPS on the system? Is it like together with a receiver?
GPS and RTK modular are mounted on induced coils to protect against strong wind and other factors and to facilitate the accurate location of anomaly bodies. Okay,
thank you. We will start the second half of the session now with our keynote speaker. Our keynote speaker is my co-chair, Jan Francke. Jan has spent the entirety of his 33-year career in geophysics trying to understand how and where ground-penetrating radar works. He runs Ground Radar, which designs and deploys custom GPR systems, as well as Geolytics, a cloud-based GPR and geophysics processing platform. He has worked in over 108 countries and holds a BSc, MSc, and PhD in GPR-related geophysics. Jan frequently lectures at universities and conferences on managing expectations with GPR technology, a task made more challenging with a tool which is often misunderstood and oversold. Jan, please take it away.
Great. Well, welcome, bienvenue. Thank you so much, everyone, for being here. I know it's weird times of the day. I'm just looking at the list of participants right now, and I'm pretty sure that we've got somebody. I mean, we've got over 100 people right now. There's somebody from every continent. So how cool is that? And for my ego's purposes, I'm going to assume that somebody's dialing on a satellite connection from an Antarctic base. So truly every continent. I'd like to think so anyway. So that's really cool. And what excites me about these conferences for the last 3 years, and I was also the lead author and lead scientist on a mining industry-wide drone research project that ended last year. I encourage everybody to go and look that up. It's an Amira project that looked at the roadmap of drone geophysics and where the technology is going. And it's looking at all these new technologies, right? But when I think about it, it's not actually how much of this is really new. Nothing's really new. It's about size and it's about lightweight, right? Like the start of all these technologies, be it magnetometer, EM, or time domain, or even GPR, usually has its start in some sort of military application. And what that required was mil-spec, bulletproof sort of size. So if you look at the average EM system today that's used for ground purposes, they're big and heavy and bulky and quite durable. And all we're doing when we're putting on a drone is stripping down all that extraneous stuff and maybe putting in a very lightweight plastic housing and lifting it off the ground. Is that new technology or is it just repurposing? Well, a lot of it's repurposing. And then the exciting part is, of course, what we do with that data. And that's true for ground penetrating radar as well. But what's really interesting about GPR is this incredible diversity of applications. I mean, think about it, the exact same technology and the exact same thing with just slightly different size antennas can be used for measuring a 3-kilometer ice cap in Greenland as it can to find cancer tumors in the human body. The exact same technology, and I challenge you to find any other geophysical technique that has that broad range of applications. So let's talk about putting GPR on drones. So there's some tremendous advantages. I don't need to tell you guys this. Obviously, lower cost in terms of large automated aerial coverage. You can survey over rough ground or over vegetation, which is often a problem for ground geophysics. And of course, for GPR, when we look at things that are potentially dangerous, like unexploded ordnance, well, having a sensor off the ground has obvious advantages, right? Now, that's the good part. There's some slight disadvantages here. You know, there's legal limitations we're going to talk about. There's significantly lower penetration, and everything else suffers in terms of performance. And that's the flip side to this. So many of our presentations have been extolling the virtues of carrying their sensors on aerial platforms. And I'm going to be a bit of a Debbie Downer because I'm going to tell you about the real physics around lifting a GPR off the dielectric, that is off the ground, and the penalty that you pay. Now, there are applications where it works, but there's a lot that it doesn't work. So none of this is new. In fact, we knew about airborne GPR, and in fact, that's how GPR was invented essentially back in the 1940s and 1950s, taking essentially what is an airborne radar system and pointing it downwards into the ground from a bomber and being able to penetrate accidentally, and that's a long story, through a Greenland ice cap and seeing the actual bedrock below the ice cap. So having an ice penetrating radar, nothing new. We knew about that 70 years ago, right? And in fact, if we look at the history of this, 1972, the Apollo lunar sounder experiment, that was very low frequency radar systems that penetrated almost 2 kilometers into the lunar regolith. Now, why was that possible? 2 kilometers from an orbiting spacecraft? Well, we have a very low dielectric and extremely arid conditions. So that is the absolute perfect radar environment. Dry and highly resistant, right? And tests from these things were done in the 1960s. So carrying a radar, and this is some of the data that we saw from the 1972 NASA experiments. So carrying a radar off the ground, nothing new. In fact, that's how radar started, right? And then, of course, glaciologists got into the game and started carrying large radar systems. Again, these are at 50 megahertz and imaging down kilometers through ice caps and seeing really fine detail. Certainly ice and glaciers and snow cover a perfect radar environment for an airborne radar system. So that's great, but there are some drawbacks, right? And one of them is the geometric spreading. So in radar, we have something called the Fresnel zone. Many of you are geophysicists, you know what that is. When you're on a dielectric that is a large number in dielectric, it tends to focus the energy. And we want focused energy as much as possible because the more wide the Fresnel zone, the more wide the aperture of the flashlight, shall we say, the more energy is being reflected back at angles away from the receiver. So we want to try and focus as much as possible. I mean, the ideal situation would be have a lased radar system, which is not possible because the size of the antenna is required. But we want to have it as much focus as possible. As soon as you lift it into the air, the beam pattern opens up about 3 times compared to being on the ground. So that's a problem. And for glaciology, when we're not looking at a discrete target, but looking at gross features and large reflected surfaces, that's sort of okay, right? That's not a big deal, and it's such a great environment. So let's talk about a little bit about this. So we have this problem of this wider Fresnel zone, which is a big issue. And of course, we have geometric spreading losses, right? Like the energy loss is 1 over R. So we have a twofold problem right there. Firstly, we have a wider aperture that's bouncing energy in all sorts of directions. We have less energy per unit area coming back at the radar. So those are 2 issues. And then we have the big problem of reflectance, right? So we're going from air, which is 1, to a material that let's put aside ice and snow because that's not really fair. That's unusual applications. Well, it actually turns out to be the best and the only application. But if we look at common ground, be it asphalt, pavement, or even clay, or any sort of typical geological media, you're going to lose at least 60% of your energy just at the air-ground interface. So we have compounding problems, right? First, we have this larger illumination zone, not getting a lot of energy per unit area. And the energy that is hitting that is being lost. 60% of that is just gone, right? It's bounced back in the first place. It hasn't penetrated the ground. That's just simple physics. That's high school level stuff. So, okay, what do we do now? Well, here's an example of exactly what happened. So this is a simple radar that I've made. It's 100 megahertz, unshielded. And it's being dragged across some glacial hill. And in the upper image, we see penetration. Yeah, it's getting down a few meters. We can see some dipping interfaces there. Now, if we look in this corner, that is the above ground reflections, right? So this is stuff that's not from underground. This is the energy going upwards. And that happens with all unshielded antennas. Not a big deal. We still see some interesting reflections here. Now, take that exact same profile, repeat it, but lift it 1.5 meters off the ground, bang, everything's gone. What we're seeing now, all these reflections, everything you see here are trees. So all of that energy is what we're getting back are above ground reflections. Really nothing's penetrating into the ground. And that's only 1.5 meters off the ground in a glacial till, which is generally a pretty good environment for GPR. So, whoa, okay, that's interesting. And that's a great example, right? This is real world scenarios. On top of that, GPR is operating in the hundreds of megahertz, which happens to be the same frequency range as quite a few of the telemetry systems that you're talking back and forth with the drone. So that what ends up happening is you get a huge amount of interference. Now, interference from the drone, generally we can kind of notch filter that out, or background subtraction, we can get rid of that. But the problem is, of course, you have such poor data in the first place, and now you're trying to filter out other interference sources. What's left behind is quite often uninterpretable. So there are all these issues from physics. And then on top of that, let's pile on the government. So back in the late 1990s, early 2000s, the FCC in the United States worked very, very hard at essentially making GPR for non-law enforcement and military applications illegal. And there's a whole bunch of reasoning behind that, not technically justified, but there was some probably lobbying from various groups to get the FCC to do that. The GPR industry worked very, very hard for years and spent a lot of money to allow most applications through. Now, the Canadians essentially copied the Americans, and so did the Europeans. So these laws are universal amongst North America and Europe, at least, and there's other countries that have similar laws. And one of the compromises that was made is that a GPR cannot be more than 1 meter off the ground. Now, at the time, that wasn't a big deal because who the hell is going to raise their GPR more than 1 meter off the ground? Well, now it becomes a big deal, right? And what we see on LinkedIn are these guys trying to lift GPR systems well over 1 meter on the ground. And the disaster here is that A, it's not going to work well at all because we know about the physics, but more importantly, we're taking a technology that was kind of barely legal 20 years ago and is still somewhat in limbo. At any time, the FCC could decide to impose more restrictions on the GPR industry, and we're flaunting what we're doing. Hey, let's lift it more than 10 meters in the, and then they're posting on LinkedIn, and that scares me. And it should scare the geophysics industry in general. There's reasons that we have agreed to 1 meter limitations. So the 1 meter thing actually kind of works because it works for the physics and it works legally. So let's talk about keeping things very close to the ground. So we have these caveats, right? It doesn't work well when it's more than 1 meter off the ground. There's severe loss in penetration everywhere except ice and snow. You have to use radar altimetry because there's a little bit of tricky processing involved if you have a variable altitude above the ground. And you have to have very good control of positioning. So, obviously RTK GPS. So having said all that and kind of, poo-poo the idea of GPR in general on drones, there are some applications that actually work. If you can get low enough to the water surface and your water itself has a very low electrical conductivity, you can get some very nice bathymetric data. So freshwater lakes or certainly rivers are great environments, particularly in places like rapids where you can't get on the river itself. And what we see is a very nice reflection from the lake bottom itself or the river bottom. So there are some interesting applications in bathymetry. Of course, this is a cheating one. This is ice and glaciers. We see beautiful data sets generally from GPR environments, which are, obviously very low dielectric, so dry ice, dry snow, and very low resistivity, or very high resistivity, I should say. Now, one of the applications that people get excited about is, I'll quickly wrap this up, is shallow mapping of UXOs, and that is potential, but there's some risks involved in terms of penetration. We can look at new types of GPR with directional antennas that try to focus that Fresnel zone and different deployment platforms as well. But I want to show you some future stuff where we're going in the next couple minutes. So we're working on magnetic loop antennas, which are huge antennas, ostensibly electrically in size. They're 50 meters long, but physically only 30 centimeters long. So this is being used for the Moon to Mars mission and looking at lava tubes on the lunar surface, but it also has terrestrial applications for deep radar penetration. This is an interesting application, looking at concrete structures from a forward-facing radar on a drone, looking at concrete cancer within the rebar structure of vertical structures that you wouldn't have been able to access easily. Another, well, the last two I'm going to show you are interesting applications for security applications. This is taking a drone with a radar system and planting it on a rooftop and watching for changes in the signature from the water content of human bodies, and being able to actually try to triangulate where people are, how many people there are, and how much they're moving. That could be useful for surveillance applications, as you can imagine. And on a similar note, placing a radar on top of a collapsed building from an earthquake, for example, and leaving it there and watching for changes in that dielectric field from changes in the water content of a human body, and being able to potentially triangulate victims trapped under rubble. So some really neat applications out there, but very, very specific. And what we're going to lead into now, and I'm just on time, is looking at 2 or 3 papers, and suspiciously, they're all about glaciers and ice, which is where radar works best. So a lot of caveats. Yes, radar does work from a drone, but in very, very specific environments. What we see on LinkedIn, the beautiful pictures of drones carrying GPRs, we never actually see the data sets because the data doesn't look very good unless they happen to be on ice. So that's my presentation. I'm going to stop sharing. Are there any questions?
Well, you explained the physics so well and so clearly that I think I know what GPR is now. Can I come to the next time? Next time you run a class, can I be there?
Yeah. Yeah, I might have done this before.
Your questions in
Great.
Q&A.
Okay. Are there any
Now
other questions from the group? Oh, wait, hold on, Drew. That's 3 questions. Oh, okay, here we go. Would it work for mapping peat soil thickness? So here we go, right? If we go back and look at, and actually there's been some recent posts on LinkedIn saying, oh, look, we're carrying it over peat soil. Yes, you are. So what's peat soil? It's essentially very, very saturated ground. So you're going to lose so much of that signal. Yes, in theory, it would work. You'd have to be essentially coupled to the dielectric, which means you need to be about 1/8 of a wavelength off the ground. So, let's say 100 megahertz, you got to be, a couple tens of centimeters off the ground, which essentially means you're dragging it on the ground for the most part. So yeah, it can work. And I guess there's applications where it's advantageous over physically dragging, but you are always paying a price in penetration. It is kind of one of the worst environments. It's basically a lake, right? So you can do it, but you got to be really, really close to the ground surface. Very educational, thanks, you're welcome. Which directional antennas do you find most promising? So yeah, directional antennas are super exciting because it kind of gets away from this, spreading loss issue. The problem is to make something directional, use a horn, right? So it's like a megaphone. It's essentially a tapered slot antenna. And well, we can't carry that because it'll be bloody heavy and huge, the size of this room. So what we do is we flatten it. And a flattened version of a horn antenna is called the Vivaldi antenna, which is still huge. So at appreciable penetrations, you're looking at 2 antennas that are the size of movie posters, if you can get that kind of size, right? So 1.5 meters, 2 meters by 1 meter. And 2 of them, right, if you don't want ringing from a monostatic system, you really want bistatic to get more power into the ground. Man, how are you going to carry that? That's going to be aerodynamically a little challenging. So the problem with directional antennas, yeah, they work and there's some physics behind them, but how the hell do we carry these things, in a practical sense? Is GPRs applicable in snow depth measurements? Yes, very much so. And that's a really good example. How is GPR, oh my God, used in geological mineral exploration? Contact me later. That's a little bit too much to talk about there. Just a comment, I was all in fire. Okay, and you're right about what happened. Okay, all right, we can read the comment later. Okay, right, quickly, velocity analysis. So this is where people go wrong. If you're lifting it off the dielectric, we've got Okay, I think we've got to end in 1 minute. If you're lifting off the dielectric, we have to compensate for that air gap, right? So yes, obviously you flatten to the ground horizon, snap everything upwards. So now you've got a flat ground, but you have to have compensated for the fact that your actual velocity includes some in the air at 0.3 meters per nanosecond plus the ground. So you have to kind of do a little bit of a back calculation, which means that, you know, typical migration routines and stuff don't work very well. You have to do a little bit more work on that. So getting that depth correctly is really tricky. You know, we're working on software to be able to automatically do that, but you do need to compensate. Otherwise, you could be 50% off on your depth. So it's really, really important you know what the elevation is, and that's why you have a laser altimeter or some sort of other sensor to tell you the exact height above terrain. Is via plastic pipeline mapping. How deep can you get when you fly 1 meter above group? Well, yes, in general, GPR has an advantage that you can find plastic pipes, but it depends on the contrast. And how deep can you get? It depends on the soil conditions. So we can talk about that later in the discussion period. But I have to go on and introduce our next speaker. So good to see you again. I saw you in Belgrade a few weeks ago. Bastien Dupuy is a research scientist from Sintif, is that how you would say it, in Norway? He's originally French, of course. And he's going to present his talk entitled Drone-based GPR Measurements for Snowpack Characterization. Hey, look at this, on snow. Funny how that happens.
Okay, nice. So yes, I will talk about snowpack characterization. So that's a work done with some colleagues at Sintef and colleagues at the University of Grenoble in France and the Norwegian Public Road Administration. On the picture here, you see a drone, DJI drone flying with a GPR, and we are in the mountains of Norway. Some surveys that we did last winter. I will show more about this. A little bit of context. So this work is part of 2 ongoing projects. The first one is a project with the Norwegian Public Road Administration. It's called Geosphere. And the second one is a project at Sintef, and both of these projects are dealing with geohazards and especially avalanches. And the goal is to see how we can use drones to forecast and monitor natural hazards and avalanches. So the main application is avalanche, road network management, but also hydropower, flood management, and glacier mass balance. The motivation is that the snow properties are show very high spatial and temporal variability, and it's difficult, costly, and it can be dangerous to record in situ data. So the tools we use, it's autonomous drone platforms, surface and subsurface sensor. I will mostly focus on GPR in this presentation. And as I said, the snow properties are changing very quick, and we need to, when we talk about avalanche forecasting, we need to get some decisions very quickly. So we want to get some processing which is done near real time. Yes, so the snow is an interesting material. First, I talk a little bit about the physics of the avalanche. Basically, to have a slab avalanche, you need 2 layers of snow, which have a different density. Usually, you have a layer with a high density on top of a layer with a lower density, and this layer with a lower density will be what we call the weak layer, and this layer can collapse, as we see on the video, the small video here, and then there is no more friction, and then you have the top layer, which is a slab, higher density that can slide down and create the avalanche. What is very interesting is that the snow density in dry snow, the snow density is almost proportional to the EM wave velocity, or to the inverse of permittivity. You see on these curves here, the snow density, there are different kind of relations, but it's almost linear to the dielectric relative permittivity. So that means that we have a direct proxy between the GPR wave velocity and the snow densities that we are interested in. In wet snow, it's a bit more complicated. Just remove this. We have the wave velocity is driven by the density, but also by the liquid water content, and you have more attenuation as well due to that, because the resistivity is lower. So we started by doing a bit of modeling, GPR wave propagation using GPR Max. We have a realistic snowpack here with different layers of different snow density, so different velocities, different thickness as well. We can have very thin layers, some centimeters thickness. And if I put back the video, and then we put a GPR in the air, and we try to see what we get. We see that we get some nice reflections. That's modeling, of course, so it's working well. And then we will see that we can interpret this in the real data. A little bit, Jan has been talking about this quite a lot. A little bit about the advantages of drone-borne survey versus ground survey. In the small video here, this is what we usually do when we do ground surveys. That's quite cool. We are skiing with a pulk on the back and we record data, but this takes a lot of time. And we'll see the main advantage of this, that the data quality is better. But for the drone survey, it's faster, it's safer. I mentioned this. If we have to go to steep terrain where you can have avalanches, of course, it's not safe to be here and record data. It's autonomous. We can cover a bigger area, and we have good repeatability as well. If we come back every week, we can fly the exact same pattern and look at changes, look at time-lapse changes. And also we can combine this with other sensors. And it's also cheaper. And then Jan talked about this as well. We have some flight operation challenges and some problems with the regulations. Here is a system that we are using. We have a RAD6 1 GHz antenna. That's the orange box here. We fly it with DJI commercial drone. We are building drone as well at SINTEF, and we will fly it with some of our prototypes, but it's not done yet. And also we have radar altimeters that's allowed to follow the terrain. We have to fly quite close to the terrain. You see on the video here, the drone is following the slope. And also it's helping for the time zero and the time zero corrections after. I will show some data from 3 different test sites in Norway. So Norway is up there. We are in the middle of Norway, and we have data from a place called Storlidalen. This is a bit of quite inland climate, so that's been quite dry snow and not so thick. We got some data from a place called Fonbu, where there is an avalanche research station of our colleagues from NGI. Here we are closer to the fjord, so we have more coastal climate with more snow, but also a bit wetter snowpack. And then we have some data from a glacier called Storbreen. That means big glacier in Norwegian, which are in the mountains, the highest mountains of Norway here in the middle of the country. So that's typical GPR data. How it looks like, that's the ground data recorded at Fonbu, so on the pulk. We see snow surface at the top. Then what you see, the main reflection here, the most energetic one, it's the snow to ground interface. Here we are again with this 1 GHz antenna, and we have very good penetration up to 8 meters here. And you see some internal layers as well, more or less continuous. It depends a little bit. So these are the snow changes, the snow layers with different density. Here the profile is quite long, almost 800 meters. So you see a lot of variation of snow thickness along these 800 meters. Now let's look at some airborne data, so drone data. We are at a place called Storlidalen, and here we have some drone GPR data. That's the red lines here. We have some ground GPR, the blue line. We have a snow pit as well, and some snow probe measurement, and also a snow depth map derived from LiDAR. What is interesting here is that we have, so we don't see on the aerial picture, but there is a slope going to the right of the picture. And also there have been quite a lot of winds. That's been at the top of the slope here. There is almost no snow, and we have up to 2.5 meters of snow. So you have big variation along these 40 meters here. A little bit about the workflow. I will show the data more in details after. Here we want to do some automatic processing. So we want that things that goes fast and that we don't need a lot of clicking on some graphical interface. So we use some Python and R routine, and we do a resampling step, T0 correction, some bandpass filtering and background removal, and then some amplitude correction and deconvolution. The last two steps is that because we want to get some true amplitudes, and then we can do some quantification on this after. I will come back to that. So that's all the data look like. At the top, that's the raw data, and at the bottom, that's the processed data with preserved amplitude. We see this slope that I was mentioning, almost no snow at the top, and then up to 2.5 meters of snow, even more here actually. You see very well the interface between the snow and the ground, so you can do some snow depth measurements. And you see some layers as well in between. We'll see that this is related to some layers that we observed in the snow pit. This is an interesting slide now. That's some comparison between this drone data and some data that we got from the pool, so on the ground. It's not exactly at the same place. You see there are some meters difference, but we see the features are almost the same. And here we can really compare the ground data and the drone data. It's exactly the same processing, same filtering, all is the same. And what we see, what we observe, I try to underline this with some circles here. You see, especially at the top of the snowpack, you see a lot more details in the ground data than here. Here we see almost nothing. You see also a bit more details deeper down, and also the signal to noise ratio is better on the ground data. Jan explained this. That's not a surprise. That's physics explaining this. But here we see really a comparison. But of course, it's a compromise. With drone data, we will fly a lot faster. We will cover a lot more terrain. So maybe it's good enough to have this data quality for us. A little bit about the flight altitude. Here we did some testing. This is at Francke, the other side. Here it's interesting because the ground under the snow, it's a lot of boulders. So that's why we got all this diffraction hyperbola. And here we are flying in quite steep terrain. Actually, it's up to 25, 30 degrees. We see the drone here. We fly inline and crossline. It was quite successful. And we did several altitude to test what's the best compromise between data quality and flight safety. Because if we fly very low, of course, we get better data, but we are flying in steep terrain and there is always a risk to crash. We have to fly very slowly and it's not that easy. So that's why we were looking for this kind of compromise. And the conclusion, it was like between 2 and 3 meters was quite good. A little bit about quantification. Again, that's nice. We have the structure, but we want to know the snow density and the snow depth. So to do that, we started to work on some reflectivity approaches. So basically, we know the propagation in the air, and then at the interface between the air of the snow, we can calculate the reflection coefficient. And this reflection coefficient depends on the contrast in permittivity. So we know the permittivity of the air, so then we can do some kind of inversion to estimate the permittivity of the first snow layer, and then we can go deeper down like this. And this is this kind of result here. It's an example on one trace here where we have 4 layers. And you see that each of the amplitudes here of each of the reflections, that's carrying some information on the contrast of permittivity. And then you can try to do some inversion and derive some information on the permittivity or the velocity. And then some information on the snow density after that. So we see here it's quite consistent with what we expect. We have a first snow layer and then a second layer, which is close to the velocity of the ice, which is a lot more compacted snow. What we can do as well is to look at what we are trying to do as well. It's to do some machine learning. I can go quite quick on this slide. I can give more details after, but basically we do some synthetic modeling of GPR traces, GPR wave propagation, and then we train a model based on this. And we get this kind. So here we have just trained the model. We have our validation set, and here that's the testing sets that I'm showing here. The red is the ground truth, and the blue is the predictions. We see that it's working quite well. So that's profiles of electromagnetic velocity. So we can derive our snow density based from that. The thing is that it's a 1D model when we do the wave propagation modeling. So that's a bit too simplistic yet. So the application to real data, it's not successful yet, but we know what we have to do. We just have to augment the data set. And with, varying the altitude of GPR, putting some noise, some 2D effects, and hopefully it will be better. So that's ongoing work, but it's quite promising. The last data set I want to show, it's for another application than avalanches. It's to calculate glacier mass balance. So some data we got at Storbræen with NVE, which is the water resource management agency in Norway. Usually to derive glacier mass balance, people just go on the field every spring and they do snow probing different places. That's all the dots you see on the glacier here. They have tested the Drone GPR, but here they were interested to see with the Drone GPR if it was working. And we did some quick survey with them, and we see very well the snow surface and the snow to ice interface. And this is what they are interested in this layer of snow on top of the ice. Here it's some quick processing that we did, just trying to do some interpolation to calculate the snow depth. And we see that of course, the resolution is a lot better than just doing snow probing like every 100 meters. So that will improve a lot the calculation of the glacier mass balance. Just very quickly, last possible application for GPR in the snow, it's to find buried objects. That's a test that we did last year in, try to remove this, but anyway, a test that we did last year in, not this winter, but the previous one with radar from 3D radar. And the main advantage of this one is that there are multi-channels, so there are several channels. And we see that when we are, we were not really flying here, we were more carrying the drone, but there's still some airborne measurements. And we see here when we have nobody in the snow pit, and when I'm actually the one doing the gain epic here, I was in the snow pit, and you see very well the diffraction hyperbola due to the person in the snow. So that's also interesting to look at this aspect. So that's the conclusion. So drone GPR for snow mapping, yes, it works and it works well. Of course, we have a loss in data quality, but we gain in safety and time. So that's a compromise, of course. We are looking at options to do quantitative processing because we want to estimate the snow density. So Bayesian inversion, machine learning, these kind of things. And also we can look at data fusion with other sensors. Part of our project, we deal also with photogrammetry and LiDAR, where you can calculate the snow depth using a baseline model. And then you can try to help the GPR data with that. And this is applicable for avalanches, hydropower, floods, and glacier mass balance. Yeah, and there it's some acknowledgements, but you can just read about it. I don't need to talk about it. Thanks.
Bastien, it's one of the best presentations I've seen on drone GPR. Really good job. There's one question here. I know you started a little late, so we'll give you a few more minutes here to answer. And it's about the use of migration in your processing. Have you looked at using migration to try and get some of those dipping reflectors in the right place? And of course, you have a three-dimensional problem, so it's a bit ingenious to just do 2D migration, but have you used it?
Yeah, we tried it, but also the problem is that we have to use a constant velocity for that, and we don't know the velocity, or we assume that we don't know it. So it didn't change much on the images when we did migration, and so that's why we didn't do it. But that's something we can do after the velocity estimation. Then we can just do some migration based on this. Yeah. When we do the snow depth, the time to depth conversion, all the data I show, it was in time, no time to depth conversion, because I don't want to I can use a constant velocity, but I don't do that. Okay,
that's great. And there's a comment about the use of step frequency or frequency domain radars and how they've been used on drones. So you can answer that if you'd like to, or I can answer it.
So we tried. I show this example of step frequency drone from 3D radar, not drone, GPR that we use from 3D radar. Obviously, the antenna was quite big, so it was not realistic to use it on a small commercial drone, at least. And the physics is the same, so it will mostly not change anything. The main advantage for us here, it was multi-channel. So for this target research for buried people, then there is a big advantage compared to single channel. But in terms of data quality for snow stratigraphy, I don't think it will change much.
Yeah, I think what people often forget when looking at step frequency or continuous wave or any other sort of waveforms or transmission regimes other than impulse radars is that you are still bandwidth limited because of the antennas, right? If you can invent an ultra wideband antenna that's actually effective at all those different frequencies, that'd be great. But you still have the same antenna. So at the end of the day, your actual, there's some advantages, but the actual data that comes out of it is very, very similar to an impulse radar. You tend to have more electronics though for any other waveform propagation, which means heavier. Okay. So Michele Maxson is from Dartmouth College, and she is going to present her talk on a novel UAS-mounted wideband frequency electromagnetic induction sensor for subsurface sensing. Wow, I'm glad I speak English because that'd be hard to say if it wasn't. It's a lot of words, man. All right, take it away.
Thanks for coming to the presentation. I'm also really happy that I got to present after all this GPR work, because I actually don't get much of a chance to work with GPR, even though I do work with snow quite a bit. So that's been really informative for me. So for what I want to look at and what we are working on is this EMI device for looking for permafrost, if you just want to shorten it up. The way that I'm going to present my information is I'm going to try to keep it simple, but anyone who has seen me present knows that I can probably filibuster Congress on this topic. So I want to try hard to stick to setting up my problem, giving you folks a little bit of EMI theory, just enough for you guys to understand the dynamics and what's happening. I'm going to talk a little bit about sensing intrusions, which is something that we struggle with in geophysics, and then the design of the sensor that we currently have and where we're going with it. First and foremost, this is not just me working on this project. We not only have theorists working on the project, but we also have electrical engineers, electromagnetic engineers, and other universities. So this is a big problem that we're trying to solve. Okay, so I've alluded to this problem. This air quotes problem that we're looking at is right now in geophysics, current sensors that we have, they don't have the resolution that we need to detect permafrost at scales that are useful. And we also don't have processing and algorithms that can account for intrusions. And when I'm talking about inclusions in this setting, I'm talking about vertical inclusions such as ice wedges, so things that are less conductive than the surrounding media. A big issue with permafrost is we have technologies that can get great resolution in the surface. We just saw some really good presentations on GPR. The thing with permafrost is you really need that good resolution in the first few centimeters, but permafrost can reach depths of 10, 20, even 100 meters. So we also need a technology that can get good resolution in the near surface, the medium surface, and then the deep. So basically the golden ticket, which we haven't found yet, but we're working on it. So people who don't live in cold environments may not really understand permafrost and its importance. So what is permafrost first and foremost? So permafrost is simply ground that's continuously frozen for 2 or more years. This is important because about 24% of the terrestrial surface is permafrost. That's 80% of Alaska has got permafrost in it. 75% of Russian landmass has got permafrost under it. And the thing is we know that the Arctic it's thawing. It is warming 2 to 3 times faster, and I've heard even 4 times faster than the rest of the globe. So as this permafrost melts, the soils, they become unstable and they subside. This causes major damage to both horizontal and vertical infrastructure. So if you also want to look at it from the climate change perspective, we also know that about half of all stored organic carbon is in permafrost. So as that permafrost melts, more organic carbon into the atmosphere, we're just kind of accelerating a process that's already accelerating. So I'm going to take now a step to do a little bit of explanation for electromagnetic induction and why we have chose to use EMI to see if we can solve this problem, the problem of detecting permafrost. In and of itself, electromagnetic induction is not super complicated. All you have, if you have a coil, and it's pretty much black magic, but it's really cool black magic. You take a coil, you put a voltage through it, and you take a current. That current in the coil will create a magnetic field around the coil. That's what we call the primary magnetic field. That primary magnetic field interacts with any conductive media that's around it. So even though soils are not necessarily highly conductive, they're still conductive. So that creates a secondary magnetic field in the soils. We sometimes call those eddy currents, depending on if you're talking to a geophysicist or electromagnetic engineer. But these secondary magnetic fields, if you put a second coil in the field of these secondary magnetic fields, you can then induce a voltage in that receiver coil, and we're able to get a response. So using the response or the voltage that we read in that secondary coil, we're able to deduce things such as the conductivity of the media where that secondary magnetic field came from. We chose electromagnetic induction because we can work in both the time domain and the frequency domain. We've already seen at least one time domain system, no, two time domain systems today. I'm focusing on a frequency domain system. EMI is nice because you don't have to have direct contact with the ground. A lot of places in the Arctic, if you guys have been there, it's not easy to walk around in. So you can also mount it in boats, so you can put it underwater. You can even use it in space. So EMI basically works everywhere. Okay, so now I'm going to ask you guys to take kind of a big leap with me here, because I'm going to have to skip forward from electromagnetic induction to some of the algorithms that we use, because I know that we have a lot of geophysicists out there, and a lot of people look at me when I do this talk and they're like, we already have systems that find conductivity in soils. Why are we trying to reinvent the wheel? So one of the big issues that we're currently facing with EMI and the algorithms is that all the solutions that we have for inverting data and for saying what the soils are underneath of us, they're horizontally layered solutions. They don't take into consideration these vertical features. So this is super important in permafrost, because these vertical features, they can be considered ice. Ice is going to melt at a different rate than the surrounding media. Again, if that ice wedge happens to be under a building or under a road, that is going to subside and cause some major damage. So the first thing I wanted to ask myself is, can we even detect it? Does the physics allow us as geophysicists to use electromagnetic induction and to detect a less conductive intrusion? So what I decided to do was, I'm using something called the method of auxiliary sources, which is a discrete orthogonal sources method. I wanted to take a look at the model, and I wanted to see if the physics will allow this. So in general, what MAS is auxiliary elementary sources, either dipoles or charges. They're placed on a fictitious surface that's offset from that true surface. These auxiliary sources, they're used to calculate the magnetic fields at the boundary. So there's a lot of math that goes into this, but on the surface, the only thing that we're doing is, if we have a primary magnetic field, so if we look at our image here on the right, we have a primary magnetic field from a coil. Some of that field is going to penetrate into the soil. Some of it's going to be reflected. Well, part of that field that's penetrates into the soil is then going to be incident on our boundary of our region 2, our intrusion. Again, part of that is going to go into the intrusion. Part of the field is going to be passed back. And there's all these like bumps that go back and forth, where you've got some of the field is going to be reflected off of the air surface boundary. Some of it's going to be passed back through. So we're able to use a full 3D model going back to Maxwell's equations, and we're able to calculate exactly how much of a magnetic field is due to the response of this intrusion in this soil. So again, stay with me while I make another big jump. So when we design our system, we already have a version 1 design. So we are now upgrading it to version 2. I wanted to show this image first. So this is what we're working towards. And I'm hoping that this, again, looks similar to a lot of folks. So you have some transmitter coils, you have some receiver coils, you have a bucking coil, and you have some electronics. I'm also hoping that some of you are like, this is super familiar. This looks like a lot of the stuff that we already built. And what I'm hoping that you guys saw was like, okay, that looks suspiciously like a potential gradiometer, which is actually what we are moving towards with this EMI device. Is rather than having our good old fashioned electromagnetic devices that we use like for sensing metals, use it in more of a gradiometer setting. So we know that gradiometers, they work really well, especially for mining exploration, mapping waste sites. We know that you can put gradiometers on UASs. We even had a whole talk about that. Again, the big crux of this is these magnetometers, what they're looking for is an item that is more conductive than its surrounding. And I want to do the opposite. I want to know, can we sense something that is less conductive than its surrounding media? So let's go back to that method of auxiliary sources that I hope all of you guys love, because I love it right now. And I built a model up. And this is a three-dimensional model made in MATLAB using good old Maxwell's equations. We have a transmitter located above the surface. We've got 5 receiver locations. So I wanted to know at these 5 locations, what is my response from this intrusion? A great thing also about MAS is I can make this shape anything I want. And since it's all modeling right now, walls, salty bags of water, or spheres. So when you look at that secondary field from the intrusion, you can see here at each one of these response locations, so at these receiver locations, you get a different response. And if you look at the difference between the response between 2, 3, 4, 5, however many of these receivers you want, you can start figuring out what is the shape of the curve. And now this is important because we are mounting this on a UAS, which means we are able to move this horizontally at a speed slow enough that we can actually build up, at least we're hoping to be able to build up these curves rather than having 5 discrete points. Also, since this is an EMI device, we can span different frequencies. So you can see the response at 100 Hertz, the shape of that response, it's going to change compared to like a 10 kilohertz response versus even a 1 megahertz response. So not only are we able to see in each individual frequency what the change is, but when you start layering these different frequencies together, you can get a very clear idea of what's underneath the surface, and you're able to look at these vertical features rather than just horizontal layering. At Dartmouth and at Krell, we actually have a system that is a handheld system that we have tested this idea on, and we have shown that it is possible to find these less conductive intrusions. So what you see here is the response from our handheld system, and it's from a 32-ounce plastic container that's flush with the surface, and it's filled with ammonium nitrate, which is an extremely poor conductor. You can see the response that we have down here. You can very clearly see the response from that. I'm going to call it a void. In my case, I'm going to call it my ice because it's so low. It's about the same conductivity as ice. So even more motivation for taking EMI and putting it on a drone. And why is it so important? Because so for this next set, what I finally did to kind of wrap up my modeling and to really make sure that we're not trying to break physics, I wanted to see if we have a transmitter, which is the red dot in this picture, and as we move it, so as like a UAS is flying, what is the response from this intrusion that's less conductive than the surrounding media? What is my sensor going to see depending on where I put my receiver? So you can see here, as we, air quotes, fly along, the change in this magnetic field, and it's also dependent on the location as well as the frequency. So where we're going with all this, I've already given some talks on our iFOSS version 1, so I'm hoping that some of you guys have seen it, so because I'm not going to spend too much time on it, even though, like I said, I could probably spend 2 or 3 hours talking on it. The iFOSS version 1, it is a lightweight land-based system that's already been built. We have also shown that it can detect these bulk conductivities and changes. So you can see here, the picture on the left is our iFOSS. iFOSS is the in-flight rapid observation surveying tool. You can see it on the left. It is a transmitter coil as well as a receiver coil. The receiver coil is actually inside of this sono tube. We took it up to Alaska, and we collected data over permafrost so that we could see if there was this bulk change in conductivity as the permafrost got closer, nearer to the surface, and as it degraded away from the surface. And as you can see, the data that we've collected shows just that we can sense the depth of this permafrost. So where are we going with all this? You saw my old iFOSS version 1. It was in a sono tube, which was near and dear to my heart because I'm a researcher, but we learned very quickly that we had to ruggedize and make the system more robust. What we've decided to do this coming year is we are now making a single transmitter and receiver that's going to transmit and receive on just one frequency. We are also driving it with a built-in FPGA board. It is a red pataya. What that red pataya is going to do is it's going to be able to sense on the fly and in real time what phase and what amplitude has to be sent to the bucking coil in order to null the field. So this is important because when we place this on a UAS, there's a lot of electromagnetic noise that the UAS is gonna emit, as well as the surrounding environment. So this is going to make it so that we don't have to, every single time when we go out there, we don't have to change the location of the bucking coil. We don't have to change the amplitudes. The FPGA board is going to be smart enough to do it on the fly. So now that I've said in the past that we've got a lot of teams working on this, one of the teams is actually our flight team. So as we're currently building the system, we have a secondary system, which is also a frequency domain system that our flight crew has been working on to make sure that when the system is fully built up, we will be able to put it on a UAS and lift it. So this is a video of our other system in flight. And this is the same dynamics and the same setup that we are having for our new IFOS system. And it's been super interesting to see all of the drones carrying the different platforms and seeing that we're all dealing with this same swinging issue, if you will, and trying to compensate for that in the data. So I'm really hoping that as a community, we're going to be able to find a silver bullet to make these things easier to fly. So overall, EMI is pretty convenient. It's cheap, cost effective. We know how to build the electronics. Lots of preliminary data show that it's possible to do. And we have tested the UAS for stability. So here's my information. If you guys have any questions that you don't feel comfortable asking me today, you can send me an email.
Again, as I said before, he's from the Lunar and Planetary Laboratory at the University of Arizona, and he's going to present a talk entitled Retrieving Debris Thickness on Debris-Covered Glaciers Using Drone-Based GPR. Roberto, take it away.
Okay, thank you. Well, first, I would like to mention that we slightly updated the title. We got new data after I submitted the abstract, so now it's Retrieving Subsurface Geometry, not only debris thickness, on debris-covered glaciers with drone GPR. So this work started last year on a rock glacier called Sourdough in Alaska, and it was a research performed by Michael Christopherson and Professor Jack Holt. This year we made some upgrades to the system, and we went first to one of our test sites in Alaska in the same rock glacier Sourdough, and also to Wyoming in August. And here are the participants. So the motivation for our work is the following. We know that there are hundreds of meters of buried ice in some locations on Mars. And we know that because we have radargrams from a sounding radar called Charad. However, we would like to know how thick is the supraglacial debris, how old and purity is this ice, if there are climate signals, and also to understand which are the best geophysical methods. We don't have the resolution to do this with a sounding radar. However, we have already some missions on Mars, for example, a rover with a GPR and Ingenuity, which is a small drone that is taking pictures, that prove that we can bring this technology to this planet. There is no evidence of Mars in Jezero crater, which is where this Mars 2020 mission is located, but at least we have proven that it's feasible to bring this technology and to explore regions with more ice. So to do this and to prove that drone-based GPR is possible to explore these debris-covered glaciers, we use terrestrial analogs. As we can see here in the image on the left, we have Sourdough rock glacier, and on the right, we have a viscous flow feature on Mars. So just to explain a little bit what are rock glaciers and debris covered glaciers. So we have a layer of debris on top of clean ice. As we can see here in the image of the left, we have, and this is an exposure of ice. So we have a meter or more of debris on top of this clean ice. And in this cartoon is an illustration of a proposed model of the formation of Galena Creek Rock Glacier, which is our second test site, where besides the debris on top, clean ice, we also have some inglacial debris bands. Our team has successfully employed traditional GPR techniques over these two rock glaciers, and actually we can see here a radiogram that was produced using sensors and software Pulse Echo. However, this is a manual task that involves walking on rough and steep surfaces. It's hazardous, and as you can see here, this equipment is heavy. It's hard to work on those regions, and also there are areas where we cannot access on foot, so we just have data gaps. We overcome these limitations by using a drone-based GPR. It's a Matrix 600 Pro with a radar Mala Drone 80 of 80 megahertz center frequency, impulse of 40 megahertz bandwidth, a weight of 3.23 kilograms. As for the navigation, we have an automated flight path. We have a radar altimeter for true terrain following, obstacle detection, avoidance radar, also live feed video. And as for the parameters, the speed, we have tested at between 0.5 to 1 meter per second, and the altitude is between 1.5 to 4 meters. Here is a video of a region where we wanted to test both the surface coupled GPR. Here we can see some people performing that survey, and also the drone, which is going towards this area of started, which is right here. As for the configuration of the drone GPR, first we have the drone on the air. So the first reflector we get is from the surface. Then we also get a reflector from the debris ice interface. And finally, we can get reflectors from the bedrock. Here is a result that we obtained from Sourdough Rock Glacier. This is a terrain adjusted radargram. As we can see here, we can see the surface at the top. Then we can identify the debris ice interface, and finally, when we were approaching the terminus of the rock glacier, it was possible even to detect the bedrock. Here are the interpretations. So we calculate the debris thickness based on the time travel, and we use a speed of 1.1 meters per nanosecond. This is derived from the permittivity of the material, and also assuming that we have clean ice here, we can detect the ice thickness using a velocity of 0.15 meters per nanosecond in this region at the bottom. As I just mentioned, at the terminus of the rock glacier, it was possible to detect the bedrock because it was thinner, the ice. So we managed to do that. Also, I forgot to mention, there was a sub-debris creek, and we were sure about that because the water was flowing. We were able to hear that, and we were able to detect a stronger reflector at that area too. Additionally, in the same region, we wanted to test if we had the same results in different orientations. So we have a line A, which is this one downhill. Also, we have a line B, and we also made a grid. And on the intersections, we tested the difference between of the total depth. This is the debris thickness plus the ice thickness when it was detected the bedrock. And we calculated the difference between the result that we got of total depth, for example, in line A with the grid, in this point, for example, here. And we obtained that the difference in all cases is less than 1 meters. Here I would like to mention that there was a tree here and the obstacle avoidance was activated. So I completed the flight manually. So that's why you see here that these points are separated a little bit more. So that's the reason, like the constant, the speed wasn't constant at that point, but still the total depth was similar to what we obtain in the different lines. As for the other rock glacier in Galena Creek, there were some expeditions where our team used surface coupled GPR in previous years, which are these regions here at the top of the rock glacier. This is the cirque. And this year we decided to make a dense grid at this part, which was the one I showed in the video. And also, I would like to mention that, for example, these lines here at the end wouldn't, I mean, they weren't possible without the drone. It wasn't, it was very steep. It wasn't possible to walk with equipment on that region. So it was a great accomplishment we had this year. Also, the base map was obtained with drone photogrammetry using post-processing kinematics and precise point positioning. So this allows us to make a change detection if we keep monitoring this regulation in the coming years. As for this area, we had here two radargrams. The one in the left is from the drone. The one on the right is from the surface, coupled GPR. First, I would like to mention here that on the drone, there is one difference. We first need to make the interpretation of the surface, whereas in the surface coupled GPR, we just assume that the surface is at time 0. But here we're focusing especially on see how accurate was the drone compared to the surface coupled GPR for the debris thickness, and also if we were able to detect these in glacial debris bands. And actually, as you can see, is pretty similar. We were able to see both debris bands that we identified with the surface couple as well. Here, this is a comparison for the points I just showed. So we see that the error between one and the other is within 1 meter. And here we have a terrain profile that we obtained using well, with a high resolution photogrammetry. It was a flight at 30 meters altitude because we wanted to have a sub-centimetric resolution in order to identify the furrows at ridges. So as you can see here, there is a compression of the debris. So we also wanted to see that if it was possible to detect this behavior, and we made it at that altitude. Also, this allows us to identify individual rocks, rotation, and lichen coverage if we have these good pictures, right? And finally, we identified on the radargrams that there is some clutter. This comes from the reflections of nadir. And one of the goals we have now is, as I mentioned before, there is the sounding radar on Mars. And for that, our team is in charge of running the clutter simulations that help to make the interpretations of the radargrams. So now we would like to adapt that clutter simulator for drone. It was also used on airborne, so we think this is possible. So it's now one of the tasks to see if we can see down here is actually clutter or if it's real data. But that's one of the task we have from now is to adapt this clutter simulator for the drone. So for that, we need a high resolution DTM obtained from photogrammetry. As for the future work, we need to increase the coverage on these two sites in Sourdough in Alaska and Galena Creek in Wyoming. Also, we'd like to make a dense grid and 3D migration, move to a new studies, maybe, for example, with thicker debris. And as I just mentioned, adapt the clutter simulator for sounding radar to drone radar. As for the conclusions, well, our system is a promising method for surveying rock glaciers on Earth. Also, we identified that high resolution imagery reduces ambiguities in regions of the GPR survey. So as we can see here, we're flying the drone GPR, and also we're obtaining photogrammetry, because also the DTM is very important for interpretations as well. And finally, the study of robotics-based platforms aligns with the interest of development of uncrewed and also crewed missions to Mars. So that's my presentation, and I will be happy to answer your questions.
Great, Roberto. Thank you so much. That was a great presentation. I don't think we have any questions yet. Oh, here we go from Colt. Quite sorry, Roberto, what is the depth difference table you showed? Are most of these values within the error budget taking into account the assumptions of velocity that have been made? So that's, I think, where you did your tie lines.
Is this one, I guess?
Yeah.
Yeah.
Or within the error budget is.
Well, yeah, the point here is I calculated the minimum resolution, which is the wavelength in air. But the problem is, for example, we don't know at that point how clean is the eye. So we cannot say like the speed is let's say 117 or 0.115. So it's hard to calculate that resolution. But I mean, if we assume this minimum resolution, which is based on air, yeah, we are very close to that.
There's another factor. You're displaying all your radar data straight down, but of course radar doesn't know about gravity, right? So the radar is actually projected normal to the surface, and we start getting more and more steep slopes. It's not at all downwards. It's normal to that surface, and it's very much three-dimensional. So I suppose some of your changes in your timeline or your tie lines could be attributed to that slight angle difference in the Fresnel zone, the illumination zone being normal to that surface.
So yeah, that's also something to consider.
Yeah. And another hint I might give you is if you're looking at clutter rejection or clutter identification, if you look at the frequency content of the clutter coming from the air, it is quite narrow band. So you could do a notch filter, for example, just to attack that clutter. It does impact your near surface data, but you could identify exactly which one's clutter. Clutter is going to be very narrow band at exactly the bandwidth of the antenna, whereas the ground is more dispersive.
Okay. Yeah, actually, what we did part was also to we identified where the location was, and we calculated the distance using in this case the air velocity. So we have the circle. So that's another way to identify it. So yeah, let's see. There are some ways to do it, but yeah, so far the interpretation is that's cluttered on that area.
Right. How high off the terrain were you?
Excuse me?
What's your elevation off the terrain? How high was the drone?
Oh, for example, here in Sourdough, we started at 2 meters. The problem are the boulders mainly. Yeah. And also, and some parts is very steep. So depends on the vertical speed of the drone. I mean, it's hard to follow the terrain. So that's why you have to go slower. But yeah, the main problem we had is the big boulders. So that's why we cannot go closer to the surface as we would expect or wanted initially, right?
Fair enough. Are there any other questions? Yeah, Jeff has one for Roberto and Bastien. Roberto, can you read this, or should I read it to you?
It says, please describe your drone terrain clearance control system for sloping ground. It's being maintained at a constant. Are you using commercial product or your own programs to control terrain? Well, in our case, we are using commercial altimeter from UGCS. Is this one right here. So what we did was we put the altimeter the front. Actually, there is no angle, is pointing at here, and also in front of that is the obstacle avoidance is from the same system. It was of the same system. So yeah, both are from the same brand because as I mentioned, we have boulders and trees. So we thought it was also very important to have that too. So yeah, it's commercial.
From Latvia. Yeah, and I think Bastien, I don't know if he's still here. I'm pretty sure he's using the Latvian SPH flight controller and collision avoidance system as well. Great, thank you very much, Roberto. I'm glad we were able to fit you in.
Yeah, my name is Johannes Stoll. I'm grateful that I get the opportunity to present my company in the last minute. MGT was founded 11 years ago in 2011. And since that time, we had the opportunity to become engaged in several projects which allowed us to travel to several destinations throughout Europe, Middle East, China, and North America, and one project in Ecuador. Also one in South Africa. From this experience, I think I got from these projects, I'm very happy that these allowed me to get a little bit deeper into this fascinating world of drone geophysics. But I have to admit that when I started this company, there was nothing, no very reliable drone and no lightweight sensors available on the market that can be fixed to the drone very easily. So I had to start from the scratch. I was very happy because I found very enthusiastic people who helped me to develop something in the very beginning. And I also want to mention in 2014, I was approached in March 2014 by Ron Bell for the first time, who found my very poor developed web page and got on the phone and called me. And since that time, I'm now discussing a lot of things around drone geophysics with Ron Bell. And I'm also very happy that he introduced me to the growing society of drone enthusiasts. So it's very interesting because now we know that there are a lot of mini drones, but at that time, of course, there were already some mini drones, but they were not reliable enough to be used in commercial projects. So I found a company, a startup company in Switzerland. The name is Aeroscout, which had developed a 75 kilogram helicopter run by a fuel engine. And we did our first project, not in Central Europe, but in Turkey after the collapse of a coal mine. And the management of the coal mine was didn't know how they can get access to the open pit, so they tried to find a company who was able to fly geophysical sensors over the collapsed mine. And I was one of the first who were called, and we were asked if we can come to Turkey within 48 hours, and we did. So this was our first project. Since that time, drones became very, very common, and which allowed us to introduce a single magnetometer, and in 2012, for the first time, a EM instrument consisting of a 3-axis induction coil system and data logger. The total weight of this EM system was almost 13 kilogram and was hardly lifted by this helicopter from Aeroscout. But with the time, we were able to reduce weight, which allowed us to integrate it on smaller UAVs. Since we are using fluxgate sensors, we can integrate not only one, we can also make use of 2 or 5 fluxgate sensors, which we use for near-surface geophysical projects. In 2016, a research group was established in Germany, which developed the so-called semi-airborne electromagnetic method to develop it for mining projects. And we were asked if it's possible. These sensors were very, very heavy at that time and could be only carried by a huge helicopter, a Sikorsky. We were asked if we know a way to reduce the weight and may integrate it on a multicopter, on a 25 kilogram multicopter, and we did. In 2018, we did our first pilot project with a self-developed multicopter designed to carry at least a maximum of 10 kilogram and fly with that load about 30 minutes. So other ideas came up by using a bigger helicopter, 125 kilogram helicopter, to do electromagnetic surveys on larger areas. The helicopter you see here in one slide, the big helicopter, can stay airborne for at least 1.5 hours. In 2020, MGT transformed into a limited liability company and also established a partnership with a UAV manufacturer, Hanseatic Aviation Solutions. And together we are developing multicopters of almost any size and also fixed wing UAVs. And here you see one of our drones in a project in North Norway. And last slide, we are now trying to design a system, an EM system that shall be carried by a fixed wing UAV, a 25 kilogram fixed wing UAV, which carries a 5 kilogram EM system consisting of the data acquisition system and a 3-axis induction coil system. Finally, I want to emphasize that we are now looking for enthusiastic geophysicists to help us to do data processing of EM data and 3D modeling using a commercial 3D EM modeling code, which allows to model and invert MT data and also controlled source electromagnetic data. Thank you.
Thank you so much, Johannes. I'm glad you were able to make it. Right. So, Laurie, do you want to switch over to the title slide there? I think we're moving on to our group discussion and summary. So I think we're going to open up the floor. Is that right, Laurie?
That is correct.
We still have quite a few people online.
Yeah.
I think the presentations in the second half and certainly the first half are very thought-provoking, and I'm sure there's lots of things that we'd like to talk about.
Jeff Pettifer here. Jan, I want to put you on the spot a little.
Please do.
You're on the guidelines committee.
I am.
For GPR. I'm wondering if you could give a perspective on how much you think guidelines for radar are needed, given that we've had this problem with ground radar, where lots of service locators and so forth may be misusing radar. Do you still think there is enough people that are going to pick up radar systems and try and use them without having the sort of erudite sort of research background that we're seeing in some of these presentations? I'm just interested in your comments on that.
It's a difficult thing to regulate, right? Yes, absolutely. I think there are guidelines that are necessary. Whether people will even bother to use them is another question. So what we're seeing, and this is a repeat of actually at the nascent time of GPR 30 years ago, the first commercialization of them becoming popular. They were in the 1970s and 80s, they were in the hands of universities. And by the late 1980s, we were able to buy them because the price had come down to $30,000. And the immediate reaction for those that were not used to GPR was, wow, we can do everything. We can survey anywhere. We can see through clay. We can see through salt water. And it turns out, you can't do many things with it at all. Otherwise, I wouldn't be on this conference. I'd be sitting on a beach in Tahiti. It's very limited. And that realization came within about 3, 4, 5 years of the commercialization of GPR. And we're seeing the same thing with the drone GPR. The initial response is, look, we can now lift GPR off the ground. We can do everything with it. And I'm starting to see, and particularly looking at LinkedIn posts, that there's a little bit of a tail coming off, and people are saying, yeah, we can do everything with it, but I'm not going to show you the data. Well, because it doesn't work in the first place. So I'm hoping that's a self-correcting issue, that the oversellers will have to self-correct because they just can't keep producing garbage data. And people who are not familiar with geophysics and not familiar with the simple physics around radar will come to realize that they've purchased something that they really can't use outside of glaciers or ice or very specific environments. So I believe it's self-correcting. One of the issues, though, with GPR is that huge diversity of applications, right? So it's very hard to write guidelines in terms of frequency recommendations or line spacing because there's so many diverse applications. So I am honestly struggling with putting together a similar document that you've been able to do and such a good job with magnetics because of the diversity and without getting into the physics behind it and essentially writing a textbook. So it is a challenge indeed.
Well, we're certainly looking for people to help you with those guidelines. So that'd be great. Yeah, and your guidance would be much appreciated. Thank you.
Hoyt has a couple questions. Actually, he has one for me. Have you tried using drone-based solutions at a land-water interface across a river or lake? Yes, indeed. I showed some examples of that. So ostensibly, radar works very well through fresh water being the operative word, right? So very low EC. The challenge, though, is that you have to be extremely close to the interface. So you have to be skimming the water. Otherwise, we go back to that physics issue of having too much bounce back and too wide a Fresnel zone. So yeah, it works. And there's lots of applications for that, particularly in difficult to reach aquatic environments like river rapids, for example. But you do have to know what you're doing when it comes to terrain following and keeping that drone extremely close to the water, if not almost touching it. So, yeah, doable. Other questions? Other discussion points? Okay, are the speakers still here? Is Roberto still here?
Yeah, I'm here.
Hello. I have a question for you, just to keep the discussion going.
Yes.
Scattering. Tell me about scattering at those wavelengths. Are you worried about? I've never been on a rock glacier, but the rocks seem rather large. And are you concerned about losing energy just from scattering? I would think at 80 megahertz that would be a concern.
Yes, actually, that was one of the first discussions we had, and that's why at the very beginning we started like, okay, let's do this as close as possible. The problem was the drone was very slow. We were like using so much battery for small regions, but turns out that I think, there is a mixture of debris and air in that layer of, let's say, 1.5, 2 meters, that even at altitudes a bit higher, let's say 3, 4 meters, you can still see at a very important depth. So I think it's the mixture of material we have there that allow us still to penetrate through that layer, and then we get to the ice. But yeah, I think the fact that is, these are rocks on top of ice, I think it's helping a lot, at least for our purposes.
Does the university actually own the radar, or have you just rented that from Guidelines?
No, this is our system.
Great. So one thing you could do is actually go into it, and their antennas are just simply a resistively loaded dipole. So it's a series of wires with some resistors on it, and you can look it up, or I can give you the equation. You can make your own antenna and stick it on there. Now, the transmitter waveform is not going to be ideal for that, but you can still essentially fake even a 45 megahertz system with longer antennas and go out and try that. It's very easy to do.
Okay. Yeah, because for example, for the surface coupled GPR, these sensors and software, they have the 50 megahertz, 100, and then the 200, but we don't have this chance yet with the drone. So we are limited. At least most of the acquisitions they have are between are at 50 and 100. So we are in the middle. So that's good, right? But yeah, I mean,
you can adapt yours.
How to get different frequencies will be ideal.
It's super easy. I'll tell you how to do it.
Okay.
Okay. Bonjour, Bastien.
Yeah, just a comment about this having bigger antenna. That's nice, but then you might face problems with drone stability and flying. So yeah, you have to try. But
that's not my problem. I just make the radars. Yeah, sure. The antennas do get large. We're actually your guys at Grenoble have I just made them a 40 megahertz radar that they're attempting to fly this week, and I assume they're going to crash it. I have no idea how they're going to lift this thing. Great. Other questions? Any ideas? Jeff, you're good to see you.
There may be a couple of questions, comments in the Q&A that we haven't covered.
Right.
Gary Young, I guess that's a comment.
That's a comment, yeah.
Yeah.
Gary's been around a long time, and he was involved indeed. Yep, I recall that. I think we've already talked about the velocity analysis issue when it comes to drone GPR and that air gap, right? Trying to flatten that out. So that's something for both Roberto and Bastien to consider, and I'm sure they're onto that. Plastic pipeline mapping, we've addressed that. There was a question up here about how can GPR be used in mineral exploration. That's a subject of a book. Oh wait, I think I have.
Yeah, you did cover that.
There's lots of papers on it. You know, primarily you're looking at shallow mineral deposits that are electrically resistive environments. So one of the things that I always try to get across when teaching this concept is that we have this impression that GPR and water don't mix, or GPR and clay don't mix, and that's absolutely garbage. GPR works absolutely fine in some clays, not all clays, right? So here in Canada, it doesn't work well. It's transported clays, they're very conductive. But in tropical environments, for example, so looking at things like nickel laterites or even iron ore deposits or bauxite, for example, in Australia, the clay has been pretty well leached of its conductor mineralogy. So you still get very, very good penetration, and we can get dozens and dozens and dozens of meters through clay in tropical environments. So I often, at the start of lectures, I often show a map of the 108 countries that I've personally worked in. And it's suspiciously, between the two tropics of Capricorn and Cancer, because that's where the radar works really, really well. And even in Australia, Jeff, all my work is up in Goben and in Weipa, and almost never in the lower states, and there's a reason for that. So there's lots and lots of applications of GPR mineral exploration, but pretty specific to the right.
If I might comment, there's a great application in iron ore mining where you get cavities formed by the natural process of shrinking of the minerals, the mineral process. And sometimes those cavities are empty, and sometimes those cavities are clay lined. And both of those, and those cavities are big enough to bog one of those big mining trucks, which just totally stops the bench operation. So we have investigated that using the OHM mapper and a GEM2 system. But it just struck me now that it would have been great to have some of the radar technologies that I've seen on these presentations as well.
Unfortunately, I've been in the Pilbara for 25 years doing exactly that. And the near surface geology is incredibly conductive. So what ends up happening in the pit face is that you're not getting much penetration. All of the reflections you're getting are from above ground, right? So you see all your pit benches. So then what you do is and you have the space to do it, you make a massive shield around it, and you have a screened antenna, which is heavy and bulky. And you do get some penetration. Back in the day, they were using just an EM31 walking back and forth and mapping it out in Geosoft. What the radar can do is nothing compared to what the EM was producing. So we've never had luck. Now, recently, a company has tried to use a drone-based GPR in the open pits in the Pilbara and had zero penetration, which we could have told them a long time ago, because it barely works on the ground, let alone all the problems of lifting it into the air. So unfortunately, no GPR. Yes, it sounds ostensibly like it'd be a good idea, but it's just too conductive for GPR in the Pilbara anyway.
Well, in this particular case, when you strip down the benches and you've got a working bench and you're very highly resistive, we're talking thousands of ohm meters. When you
In the
actually
BIF itself, in the channel narrative, in the CID.
Yeah, once you strip all that overburden off and you get down to the actual ore, and you're worried about, they might be out wanting to take several meters off that bench, but they're worried about the next pass.
Yeah,
things like that. So yeah.
With modern real-time sampling, probably again from a ground-based system, it might be possible, but it has been tried literally in the pit bench, in the pit floors at Tom Price, Parabadoo, all over both BHP and Rio Tinto mines, and we've never seen anything that's that impressive, despite that high resistivity, which is kind of surprising. Now, other iron ore deposits, Simandou, beautiful, 10, 20, 30, 100,000 ohm meters, beautiful. The BIF deposits in Brazil and West Africa are great for GPR. We can see a lot of information there going down hundreds of meters. Just never seen anything good in the Pilbara at all.
Yeah, and there is a question also from Ed Kenyon and
oh, here we go.
The last, yeah.
Yeah, okay, a general question for Jan. For a GPR from a non-engineer, perhaps also outside of GPR. Okay, seeing that mobile phones use them, what would using fractal antennas or coils for TX and RX be applicable to increase their length and effective size while maintaining? Yeah. So can we look at different types of antenna designs? Absolutely, absolutely. And I think that's where the big step is going to be in drone GPR. It's very easy to essentially take a ground GPR, strip off all the encasements, and still have a resistively loaded dipole, because that's what works. And it's a good lossy antenna, and it's been used since the 1960s, and it's light. So dipoles work, but they're not very directional, and they're not super efficient in the direction you want to be going in. So yeah, can we use things like fractal antennas or even circular plane antennas? Yes, and that's what I've been looking at. Actually, I have. There's one there. I can't get it right now. But there's some really neat antenna designs, but it becomes an aerodynamic issue then, right? So as I was talking about with Vivaldi antennas, they hold tremendous potential. They're very directional, they're very efficient, and in theory, they're very light because they're just a strip of copper. They're just bloody large in the planar size, right? So how do you fly the thing? And the same thing with fractal antennas. In fact, you can combine the two and you can do something called a palm tree Vivaldi, which is a combination of a fractal and a Vivaldi. But the fact is the throat, the mouth size of the Vivaldi needs to be, it's relevant to your wavelength. So for looking at things that are, Roberto's doing at 80 megahertz, the bloody thing's going to be huge. It's 1.5 meters by 2 meters tall. There's no way around that unless we leave electrical antennas behind. And why can't we excite the EM field from a magnetic antenna? And that's, I think, the step change that's going to happen. So right now there's an AMARA project, and there's some backing from some space agencies that has been going on with myself and RMIT with Jim McNay. I'm sure many of you know Jim, trying to develop, and actually we have developed it, a very small, compact, 30 centimeter long magnetic antennas, which are down in the dispersive field. So they're from 300 kilohertz up to about 3 or 5 megahertz. So very, very, very low frequencies. And they work-ish, but anything above about 10 megahertz is becoming incredibly inefficient. So, what are the applications? Probably very deep glaciology, Antarctic, multiple kilometer sort of penetration applications, or deep mineral exploration. But magnetic antennas have their limitations as well, unfortunately. So yeah, if you can invent an antenna that's light and broadband and small, yeah, you get a PhD for that.
Yeah, so you just mentioned that this magnetic antenna allows you to have frequencies similar to the ones I am using now, or it's lower?
Way lower.
Okay.
Way lower, order of magnitude lower. So we're looking at 3 megahertz, right? And that's the problem. You're right at the edge of the propagation, the radar plateau, we call it. So it becomes a dispersed field. So RMIT is looking at the EM modeling side of things. So it's essentially a hybrid EM/GPR antenna, but at incredibly low frequencies. And there's applications for that. There's obviously lunar exploration applications, but there's also glaciology applications, but it would not have the resolution that you need, unfortunately.
Okay. I have a question when we talked about the clutter. And okay, well, initially this clutter simulator was designed for airborne radar on Antarctica, then it was adapted for sounding radar on Mars. So it's like very low resolution in both cases. And when we found the same problem, let's say on drone radar, okay, we realized, okay, we need a trajectory of the spacecraft, or in this case, the drone, and we need a DTM, right? So we know where the reflectors come and stuff. And you mentioned there was another option for that. What's the technology, or what could we develop instead of trying to replicate this clutter simulator, as we call it?
Yeah, so this is a very common problem with low frequency that is unshielded GPR, right? Particularly in environments either where you're lifting the antenna off the ground, it becomes omnidirectional, or where you're in a conductive environment like the Pilbara, where we're picking up all the bench walls, for example, this clutter, or what we call in the GPR world, airwave reflections, right? So the nice thing about airwaves is that A, they're predictable. If you have a very good DTM, you should be able to model where they are. One of the applications that is very challenging is along certain borders looking for tunnel detection. And it turns out that in the 3 border areas in the world that are highly susceptible to tunnel detection, that is the southern US border, Israel, and parts of India, it's bloody conductive ground. So yeah, radar sounds like a great environment. It doesn't work very well because of all the clutter of this airwave reflection. So a lot of time and effort's gone into, hey, we know where the fences are, we know where the walls are of the border. Can we predict which reflection is clutter and somehow subtract the two? And it's really hard to do. Like, it's being tried, and you know, it's in theory possible, but in practice, well, really, really hard to do. So then you look at the clutter itself, and it turns out that the ground, when the radar goes into the ground, it somewhat disperses. So its central frequency broadens out a lot. Whereas when it bounces off something in the air, it's quite narrow band, or relatively narrow band. So can you identify the frequency content of the clutter and do a notch filter just for that frequency? It's going to bugger up the rest of your data for sure, but at least it clears up that clutter. And it's something that's really important, like finding a tunnel underneath the border, then you might be able to afford that cost in data fidelity by doing a notch filter, essentially. The other thing you can do is clutter, depending on the geometry, tends to be migratable. You can migrate the data at 0.3 meters per nanosecond. Surprisingly, a lot of the clutter disappears.
Yeah, because in the case of the clutter simulator, what you have is an additional product. So when you are analyzing, okay, you can see, okay, this is how the clutter simulation looks, and this is my data, so I can visually determine whether or not it's clutter. But in this case, you mentioned is you are actually updating, let's say, the original data, right? So you pass the filter through the data, and okay.
And actually, the other thing you can do is take a window of each trace and do an instantaneous frequency plot. Just do an FFT on a small window and display that. You can do that in GeoSoft. and what you'll see is where the clutter is, it'll have a very distinct frequency. So you can just visually identify, okay, that's clutter, and it's unlikely to be from the subsurface. So that helps in your interpretation as well.
Okay.
Yeah, thanks, Jan and Laurie. I just want to remind everybody that's on the call that we have on November 12th the first of several webinars on drone geophysics guidelines, and this one will be concentrating on magnetics, and there will be publicity going out through various societies to try and get end users of the geophysics, as well as users of geophysics, to tune into that, because it's important for end users to know what is good data and what is bad data, and who might be the good contractors and who might be the ones that are not so good with the data. So please tune into that, and I think you'll find it very interesting. It's a free webinar.
Okay. Oh, all right. Okay, actually, we do have, yes. Okay, yes, absolutely. So we have a question here from an anonymous attendee. That sounds suspicious. Have you heard of specific cases of drone GPR being successfully used for in collapsed structures and finding victims? Is it real-time use, or does it require post-processing? Could drone GPR be used to, say, check shipping containers? Well, no, because they're metal usually, so it's not going to get through metal. Waiting in line for trucks going to the border, have drones. Right. Sounds like a great idea for shipping containers, obviously an issue, but it won't work because the last I checked, I'm not an expert, but shipping containers tend to be metal and radar doesn't tend to penetrate metal very far, unfortunately. So that won't work. However, back to your first question about using drone GPR to locate victims. No, it has not happened. It's just an idea, but there's nothing to stop somebody from doing that. Having said that, GPR in the recent Nepal earthquake, I can't remember when that was, GPR, a team from Taiwan, I think, was deployed with the sensors and software, as well as they had some GSSI systems. And actually sensors and software, in fact, markets a specific GPR called FINDAR, I think. Essentially, it's a 500 megahertz antenna, and it has a background subtraction on. So you can do this with any radar at all. It doesn't matter, but the 500 megahertz is small, and you can lift that with a drone in theory. So what you're doing, it is real time. What you would do is have, Bluetooth or Wi-Fi telemetry system sending that data out. And all you're doing is you're parking the drone, shutting down the drone itself, and the radar is operating on a pile of rubble. Now, if nothing is moving, then you're going to have a blank screen. If something moves, well, I mean, theoretically, if the rubble settles, that's one problem. But if you have your background subtraction on, then everything's homogeneous, right? But if anything moves, even a rat, you should be able to see at that wavelength a little bit of a blip. And if you can measure the time of the blip, and you kind of assume that the rubble is, assumed velocity close to air, you can get an idea of where it is in terms of depth away, or at least range away. It could be to the side. So from a ground-based radar, yep, it's been done before and successfully done. And there's, Sense and Software actually sells a system for search and rescue systems. Now the next step is just take one of these Latvian systems, anybody can make them, and put them on a drone. And that way you don't have to have somebody actually climbing on top of the rubble to place the thing there in the first place. And if you're really clever, why just one? Why can't we use multiple drones? And it'd be very easy live to figure out triangulation to get an idea of position of where that movement might come from. So very, very easy technology. Somebody go do a PhD on it, and I'll tell you how to do it. Roberto, hello.
Yeah, this also kind of a general question. Like, for example, when you want to get a drone GPR, I mean, you have 2 or 3 options, I would say, like on commercial. That's what I've seen for drone GPR. Do you see this changing? Like, for example, it's like, okay, well, you get these 80 megahertz, or you find a one for 100 megahertz, and that's it. Do you see these growing, or there are many options out there that we don't know? How do you see the market in general for this?
I think the market is not going to grow because the market is so narrow in the first place, right? So the drone GPRs that you see are specific to, well, look, I make them, but they're not commercial. They're used for military applications usually. Lots of people can make them. The original one is, Per Wikström up in Boden, Sweden, has this, what's it called, sub-echo antennas. And 5 years ago, he went to the Latvians at SPH and said, can you lift this from a drone? And up it went. So that's all they're doing, is taking a ground-based radar and lifting it. Mala and Guideline Geo saw this as an application and made their own, which is essentially just a Pro-X system, with a simple controller board and a Wi-Fi connection. So, and I think they even have a Raspberry Pi on board. So all of those systems are just ground-based systems that are being adapted to airborne platforms. And both, if you talk to Mala and if you talk to SPH, they are doubling in sales every year. Now that's interesting because we've just shown that what the heck are the applications in the first place? And if you look at where the sales are going, a lot of them, well, to research organizations, so that's fine. We'll assume they know what they're doing. But a lot of them are also going to countries that may not have a lot of geophysical academic background. So companies that are like, you know, we find them all over the world that they're looking online saying, oh my God, I can do GPR from a drone, and they buy these systems and are, you know, subsequently somewhat disappointed in the performance or are entirely misinterpreting. So I think what's going to happen is there's going to be a leveling off eventually, right? There's reality is going to hit, and you know, you'll still be able to get the Latvian systems, and I'm sure Mala will sell a few. I know Sensen Software has tested it out because there's some applications, particularly you know, river bathymetry. That's got some commercial background to it, and there's potentially some use there, and it does work very well. So there is a niche market for them, but I can't see a burgeoning, you know, 20 different companies. I get asked once every couple weeks to make a custom radar, and I would say 80% of the time I say no, I can't. Well, actually, Bastien, I told you I couldn't do it last year because we didn't have parts in the first place. But you know, that would have been a good application. But 80% of the time, it's like, no, I'm not going to make this to you because you're going to be disappointed, and then everybody has a bad reputation. So why even bother, right? Your two applications, awesome, great, but not many people are like you, right?
Yeah.
Yeah, there is a comment that Strian has in the chat. Maybe, wow. Yeah, maybe you can actually tell us rather than us reading through if you are unmuted.
I am. So my question was looking at some of the different methods that folks are talking about. I mean, it's super exciting to see the advancements that are happening. I'm particularly excited some of the EM induction work. But one thing that keeps coming up is about that we're needing to fly in close proximity to the ground. And, you know, and I fly a variety of different methods on drones across the country. And this is a really complex thing to do in anything other than smooth, flat terrain. And it's also very atypical of the larger drone industry. And so the aircraft, honestly, usually like the commercial aircraft aren't built to actually, and I know what their specifications say, but I work with hundreds of pilots and fly all over the place myself. These drones don't hold their position that precisely. So if you're trying to fly even 3 feet off the ground, we have surveyed in that aircraft are moving 5-6 feet, you know, when they say that they are holding their position, you know, vertically. And so I guess one of my questions is, how do we as a community work with drone manufacturers, especially given we're such a small community, to build the capabilities that we need, or to advocate for the capabilities we need to be able to do this work safely and effectively? Thanks.
And I actually do. Great question. Actually, one of the things I've been really working on is ultra low altitude flights. And what we're doing right now is using a radar altimeter, and that seems to be working pretty well. We get it from SPH Engineering, so it really fits well with the EM61 because that's actually driven by the Sky Hub that HP Engineering is working with. We've collected data using the Mag Arrow and the what's that other system? GEM2 UAV, and the reality for my world is I don't have enough time in the day to do all that I want to do. So, but what I hope within the next 3 to 4 months is actually do some publications available through the, I don't know, wherever I'll publish it, but actually demonstrating how well the LiDAR/radar altimeter works. So
I thought maybe Johannes, you are still online. Maybe you have a comment as well because you have interacted with manufacturers over.
Well, actually, I also have a comment on that. Well, we are using also this SPH altimeter. However, I mean, we had to use that because we already had the Matrix 600. However, I have seen that there is another industry that also flies very close to the ground and uses altimeters, and is the drones for farming. And these, the sprayers, another solution that we analyzed at some point was like, what if we have these drones like DJI or Helio, which are made in the US, which are 2-3 altimeters with obstacle avoidance as well. So that's another option. So you don't have to work on with a matrix and then adapt the sensors and so on. So you have a solution that is built in. And I think that industry is more developed than the geophysics, and there are so many drones out there that maybe could be an easier solution, I guess.
May I play the devil's advocate for a second? And for those of us who we've tried using like laser altimeters on our UASs, and we also struggle with the same problem. And the problem, not only being able to stay close enough to the ground and hold it steadily, but since we have slung systems, if we use a laser altimeter directly underneath of our sensor, we're basically just going to get the distance between the platform to the sensor. So if there's any other recommendations that folks have on how to basically get around that, it would definitely be a big help and a solution.
Wow, that was an interesting point indeed. Wonder how it works. Now that you said that, Michele, I wonder. Bastien, you had your hand up and you put it down. You still have a comment about that?
No, it was just another comment about this radar altimeter. So we used it in quite steep terrain, up to 25-30 degrees. And we see that if you are flying up the slope, it takes quite a bit of time to update. So you have to fly very slow. And we found out that just flying 1 meter per second at 1 meter altitude, it doesn't have time to update. So we just risk to crash. That's why we were flying a bit higher. Otherwise, you have to fly very slow if you want the algorithm to have enough time to update and lift the drone accordingly to the altitude. So this is working, but in steep terrain, it's you have to be careful.
I redirect my question to Johannes about if you had any comment on this topic.
Yeah, I always did very hard to find the right technology drone for my projects. Mainly the reliability, and second, drones from big manufacturers usually have features which sometimes, for example, the DJI drone I used in one project, this is a big one, the Acro copter from DJI, had a big disadvantage because it couldn't fly higher than 80 meters above the ground station because it was designed to spray crops, and it's really a robot that can be used only for one single purpose. A second feature which led me to collaborate with manufacturers and build our own multicopter is the endurance. There are several parameters you can modify to improve the payload and also the flight endurance. I don't speak about doubling the endurance, but we are able to increase the endurance compared to standard drones by a factor of maybe 15–20%. And I think this is very important because if an area is not very accessible, but you always have to go by car to as close as possible to the area and to the survey area. But if in rough terrain, mountains, it easily can happen that you have almost no access to the area. So you have to fly, you have to put your ground station far away from the flight lines and overcome sometimes 1 kilometer before you reach the survey area. So if you use a multicopter with a very, very limited endurance flight time, you are not really able to fly this project. So this was the reason why we developed our own multicopters. In some cases, it's more advantageous to use fixed wing rather than multicopters. If the terrain is more or less flat with changes in the elevation no more than 100 meters, it's advantageous to use a fixed wing rather than a multicopter, because a fixed wing flies much faster, and the sample rate of most sensors is fast enough to allow a reasonable point spacing.
Thank you. Bruno, you have your hand up.
About the question of being close to the ground, we experimented quite a bit at NRX, not ourselves, but we work with companies building drones, and we tried laser, ultrasound, many things. And in the end, what was the most effective was because we do some archaeology to fly at 1 meter or even below above the ground, was to do some numerical model of the terrain with photogrammetry or LiDAR with 1 or 2 flights. And you spend 1 day to do that, and then you navigate with a RTK positioning. It's actually what was the most effective in the end. So if you have like a survey that will, for a duration of a few days, it can be worth it to do a numerical model, or if the client has already a 10 centimeter resolution model of the terrain, it's possible to use it.
Does that usually kind of double the cost of the project if you?
It depends on the
what
size
is
of
the
your
percent?
project. It depends on the size. If you are doing like a 1 day survey, it's not worth it. But if you are in a project over a large area, when you know that you have like 10 days of surveying, if you want to, it doesn't cost so much more.
Great. I see that there's a question in the chat window from Aaron Francke about the use of GPR or drone GPR on lava or basaltic flows, looking for lava tubes or lava tunnels. And you probably know from a quick literature search that a tremendous amount of work has been done all over the world, actually, as analogies to Martian exploration or for lunar radar simulations, right, on terrestrial lava tubes. So the nice thing about basalt is it tends to be very resistive, or very low conductivity, I should say. So from a radar standpoint, it's a great environment. But if you're now lifting that antenna off the ground, the moisture, or how wet is that basalt, becomes a factor. So doing it on the ground, great. Lifting it off the ground, you want to be as dry as possible, because if you have a wet surface, you're going to have that huge reflection coming back. There's some very good paper. I don't know if anybody's done drone work on basalt specifically. I've done some testing on a backpack radar system, again, that Mars system up in central Queensland, and got some great results, but with magnetic antennas, so very, very low resolution. But there's some good work on the Craters of the Moon site in Idaho from about 2006. They've used low frequency radar to find lava tubes there, and it's kind of a really good case study. And I can't remember who wrote it, but it'd be about 2006. And you can look that up on Google Scholar. Okay.
I can read that one and actually have an answer for that too. Is anyone trying to link being close to the ground, less than 3 meters, with trees, bushes, and other complex terrain features that require very good obstacle avoidance? Actually, on that, we realized that, for example, we cannot try to go uphill. Otherwise, the obstacle avoidance will activate every time. So that's a limitation we have. We have to either go downhill or traverse a slope and trying to do a grid. I mean, it's one of the limitations we had. Also, the obstacle avoidance have to have a certain angle so we can detect the trees, because, for example, if we are at 2-3 meters, let's say, we cannot set the obstacle avoidance, for example, at 4 meters, otherwise it will activate. And actually it worked, but yeah, we understand that we have those limitations. So for now for us, besides the fact that the vertical speed doesn't allow us to follow the terrain uphill, we have that limitation that the obstacle avoidance will trigger anytime. So yeah, that's how we dealing with that. And yeah, it's a practical solution, and yeah, we didn't have to deal with that. But yeah, it's a challenge, I would say, to deal with those two things at the same time.
And I'm happy to speak to that as well, because so a lot of the GPR work that I'm doing is over rivers. And so you're often actually flying below the pilot because the river is, or stream is often at a lower elevation than where I am. And also you have tree lines. And so honestly, in those conditions for what we're doing, it's right now we're flying manually. So it's human obstacle avoidance, because often before you hit something big, you've got very small, fine things that the aircraft that we have don't have automated obstacle avoidance. And also with that, those sorts of fine branches and twigs, they're not necessarily going to see those in a timely fashion for us. And so we're flying under canopy, we're flying off of like areas with, bushes and things like that. So that's why we're super interested in these issues, because also, DEMs, even if I did a DEM, for example, of a river in some conditions, the river elevation water level could change from one day to the next, or even over the course of the day quite significantly. So it's interesting. It's a challenging issue. So that's why it's exciting to see how people are dealing with it.
Chap?
Yeah, I'd be interested in comments from the panelists and participants, particularly those that have working with drone systems, how they're tackling this problem of a bird or sensor swing that seems to be affecting some sensors seem to be affected by it, or all sensors seem to be affected by it, and only some seem to have compensated for it. So I'd be interested to see how rigid versus flexible suspension systems. I know Ron's been working with some of these things, but maybe Johannes and others. So I'm interested to hear what people have to say.
To add to Jeff's question, I am not clear, since we can have a rigid arm to connect to the sensor, why are sling systems still in use? What is the benefit of having a sling, like a system, rather than rigid mount?
I know from our perspective, we always have a sling mount, only because when you work with I'm going to say lower frequencies, because we even have up to high frequency electromagnetic induction sensors, in order to get the standoff so that the EM noise from the UAS doesn't overshadow what we're actually looking for. So in order to get a standoff distance that was far enough, if we put a rigid structure on it, it would have just been too heavy. Ropes are just lighter than PVC pipes.
Yeah, but there's other material. You can have a Spectra tube that is incredibly lightweight. It would rival the weight of ropes.
So we have done a lot of testing with our systems, even with like carbon fiber and Kevlar, and both of those things, they actually do have a response. And the problem with EMI and with any sort of magnetic induction that we do is not only is there a response from, and it's all the way up to like 250 kilohertz, we can see it and it's very loud and we see it, but also when you have those at the angles that come like straight down, so it's actually in the Z direction, if you will, that's just it's too much feedback and too much noise.
Okay, I'm obviously carbon fiber. I'm kind of surprised that other aramid fibers or even fiberglass itself would have much of an EM response.
We were really surprised too, and we were, it definitely put a hiccup in a lot of our sensors that we were currently building when we learned that.
Right. Okay. Well, Geonics would be interesting to hear that, because most of their EM systems are encased in fiberglass for that reason. Huh.
But it has to do too with the frequencies that we're looking at. Right. I'm not sure what frequencies they're dealing with, but if you have a low enough, it does not impact. But once you get into this, the HFEMI, Max is going to talk. I'm sure he can talk more about it because his system was impacted by it.
Yeah, so on the image I showed for our Air Force, the Ultima Air system, we had carbon fiber on top and on bottom. And the second we have, the handheld variant, we also have carbon fiber. But the second one is a much smaller strip, so the response is negligible essentially. But because that carbon fiber is so large on the Air Force, on the air system, it adds a lot more noise, and we need to cut it down. And so we had those immense cutouts. Was essentially to reduce noise. Wow. So it depends on the size of them and the size of the material present.
We would much rather not sling them if that was an option.
Maybe it will be with technology keeping pace.
I'm sure a pilot would appreciate it too.
Isn't there also an issue with taking off and landing? If you have a fixed boom, it's quite complicated. You have to make it moving, then deploy it, and that's not very stable. If you need to deport it a few meters, it's maybe not the most practical.
And I can recall so the system that Max had showed in his presentation, the ULEMA Air system, there was a previous version that was much smaller. And in order to get away from slinging it, we did have a rigid PVCs, a full plastic structure, and the UAS was significantly smaller and actually landed on top of it. But once we started building larger systems so that we could, get what we were looking for, that was not an option because you can't land something that's, 5 feet tall.
Any last questions, comments?
Elizabeth, would you ask your question again? I'm not fully sure what you were really asking about slung loads. Why are you?
I said just because the sling also has some motion issue, and since it is possible to have rigid mounts, why are we still using sling mount sensors? That was a question.
Okay.
That we got a number of good answers, but please comment.
Well, the primary reason I began using a sling mount was to keep the magnetometer away from the motor noise and whatever was created by the drone. And obviously others have actually studied that, and I took a very practical approach. I looked at the mag data, and when I didn't see it move the sensor below it, that became the distance that I therefore used. But the other issue that I ran into was the movement. And so what I've taken is I've thought a lot about how to get it to be stable. And I've not only integrated an intermediate frame in my suspension system, I've also added on some tension wires that actually dampen the movement of it, and then we're very careful about how we fly it. That is, now does that remove all the motor noise? I mean, all the movement noise? No, it does not. But as Bart showed in his presentation, there are ways of actually reducing the amount of it. The first approach I took was just to figure out what that frequency was in the data. This is mag data I'm talking about. And I just, I kind of estimated what that movement would be. It does vary as you're acquiring it, but I've estimated what the movement would be, and I was able to apply a filter to it to actually reduce the amount of noise that actually came from it. The MagGirl also has an IMU, and there's data that's actually provided with the magnetic data that, from what I see, is generally not being utilized. And that's something I'm trying to get time to actually work on, as to how to actually utilize that data to develop a compensation system. Bart spoke about what they're doing at Geometrics. The other it also, some of what we're doing also applies to the other sensors, although the time domain system is so heavy that it's really one of the big issues we dealt with is to just get it light enough so the drone could lift it, at least the drone we're using. And then it became the speed of the aircraft that actually determined how much movement was actually being imparted on the sensor. But it doesn't seem like being in the time domain, it was a big issue. Being in the frequency domain with the GEM2, we have applied the internal frames and the tensioners to it, and we continue to work with that. The biggest issue that I kind of moved my attention to was I'm using a drone that does not have RTK, GNSS as a navigation system. So that's in itself is not a big deal if you're flying 30 meters above the ground surface and collecting mag data. But it is a problem when you're trying to fly your sensor 1 meter above the ground surface or less, and you want to figure out that data positioning point. I've developed, or I built an RTK GNSS system that I actually add to my drone. I don't want to get into trying to modify this particular drone. And what I learned from after my talk on Tuesday, so many days ago, Johannes told me that he's developed an RTK GNSS system as well. For the same reason, as that we recognize that it was the data point positioning as we brought our sensors closer to the Earth was starting to be a big part of the whole data value problem. Where the heck are we making the measurement, and what does that mean to our volume of data that we're collecting? So I know I've kind of extended and I droned on a little bit about the suspension system. I actually have ideas about adding some airfoils to my suspension system to actually use the forward movement and to actually stabilize the sensor as it's in flight. I've played with ideas of trying to build a gimbal so I can mount it from a gimbal, but that kind of that is mounting the magnetometer from a gimbal or a geophysical magnetometer. I've looked at drones that actually do not have any pitch forward. That becomes an issue as well, that they're actually designed to the drone will pitch, but the payload will not. And that I see as a potential solution to some of the problems that we're running into.
Thank you. Well, any last thoughts, Jan?
No, that's great. This is really, this is the best part of these discussions are really where the ideas come out, right? So look, we've identified some mechanical engineering student needs to do a research project on a semi-rigid or some sort of standoff that starts off being flexible and then makes itself rigid when it's in the air, right? That sounds like a mechanical engineering problem or aeronautics engineering problem.
Well, thank you to all the presenters and good discussions. I believe we can close the session.